These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Can you tell me, how could you simplify that?
Well, I'm not sure.
Okay. It turns out that when you are dividing two numbers with the same base, you subtract the exponents.
Okay.
So, as usual, something we have to do on each of these sections before we get started is review the algebra that we're going to need on that section. So for the next section of the textbook, there's some new algebra that we're going to be needing. There's a lot of quotients and division in this next section, so we have to deal with these types of things. All right, so this is just a fact from high school algebra that when you are dividing two numbers with the same base, you subtract the exponents. So what would this be?
X cubed.
Excellent. And what would this be?
That would be x to the 8th power.
Good. While we're at it, we may as well then review. Can you figure out what do you think would be a logical thing to do when you're multiplying two numbers with the same base?
We add them, so x to the 6th power.
That's right. And this would be?
X to the 14th power.
Now keep in mind, all of this only works if you're multiplying or dividing numbers with the same base. If they don't have the same base, then you can't use these rules. Okay. How would you simplify this?
Well, we subtract the exponents. So we would say it's 2 and something x cubed. I don't know, 7/3 x cubed.
Where did you get the x cubed from?
X squared, I mean.
Okay. So what's the answer?
7/3 times x squared.
Okay. Yeah. Didn't sound too happy about that, but that's the right answer. Yes. So that's what we do here. Good. By the way, how do you read this aloud?
That is x squared.
And how do you read this aloud?
It's x cubed.
Right. I think sometimes we have a tendency to get those confused with each other. You could just say this is x raised to the 2nd power, and this is x raised to the 3rd power. But if we're going to use these terms, that's the correct way to do it. Okay. So let's try this example.
That would be x to the 7th power.
Good. People tend to make mistakes with negative signs, so you'd want to double check yourself here. But 4 minus -3 really is 7. So you got that correct. Good. Now let's try this.
-5 plus 2. X to the -3rd power.
Yeah, again, you'd want to double check because it's easy to make mistakes with negative signs. But -5 minus -2 is the same as -5 plus 2, which is x to the -3. Okay, good. How about this?
0. 0. 0. Yeah. Well, 4 divided by 0 would it be undefined?
Okay, we probably should have just reviewed a little bit about division here to start with. What's this?
3.
How do you know? How would you check that?
4 times 3 equals 12.
That's right. And what's this?
2.
How do you know? How would you check that?
We can take 9 times 2. That equals 18.
Good. So what's this?
0.
And how would you check that?
3 times 0 equals 0.
So it works out. And what's this?
0.
And
7 times 0. 7 times 0 equals 0.
So that checks out. So what might this be?
That can't be anything.
That's right. Could it be 0?
No,
No. How can you see that that doesn't work?
because 0 times 0 is not 4.
Yeah, 0 times 0 is not 4. Could it maybe be 4?
Nope.
Because how would you check that?
4 times 0 is not 4.
That's right. So, as I think you were working out, I think you were starting to guess what's the answer here? What should I write here?
Undefined.
Right. But I tried to give you a little bit of an explanation for why mathematicians say it's undefined. I think everyone's kind of heard that you're not allowed to divide by 0, but that kind of sounds like that's just kind of like some whim that the mathematicians came up with. Well, you know, we just don't feel like letting anyone divide by 0 because we're meanies or something. So it's not like they're preventing people from dividing by 0. It doesn't make sense because whatever number you try to put here, when you try to do the multiplication, you never get the 4 back. So you could do this by trial and error. You could keep checking numbers by trial and error until you find something that multiplies by 9 to give 18. But nothing times 0 will equal 4. It doesn't matter what you put here. Nothing times 0 is 4. That's why it's undefined. Okay, good. So this would be?
Undefined.
Right. How do you know it can't be, say, 3?
Because 3 times 0 is not 12.
That's right. So, it's okay to have a 0 on the top of the fraction, but it's not okay to have a 0 on the bottom. I think people tend to get confused about that. You could figure that out using what we just talked about, but maybe we should just memorize that. 0 is okay on the top of the fraction, but 0 is not allowed on the bottom of the fraction. So this is what's called undefined. By the way, this is not indeterminate. Indeterminate is a new idea that is first introduced in calculus, and we haven't talked about that yet. We'll be getting to that soon in this section. But right now we're just going over basic high school arithmetic. So here we're just using the term undefined. Indeterminate will come later. Okay, good. So what's this?
0.
Oh, yeah, it is, isn't it? Because 0 times 0 is 0,
yeah.
I guess. I just said you can't divide by 0, though, didn't I? What does my calculator say about that? 0 divided by 0. Well, my calculator won't do that one. All right, well, now I'm a little confused. I'm not sure whether this is really 0. I got it. All right. So, you phased me for a second there, but I've got my bearings again. So you say this is 0, do you? Well, how do you know? How would you check that?
0 times 0 equals 0.
Okay. Well, you think you're so clever, but I disagree with you. I think that 0 divided by 0 is 8. So check that. Does that work?
It does.
It does work. How do you check that?
8 times 0 equals 0.
So that does work. And, you know, I have this invisible friend sitting next to me, and he's saying that he thinks that 0 divided by 0 is -5. So let's check that. How would you check that?
Take -5 times 0, and that's also 0.
Okay, all right. So I was a little worried there for a second, but this really is undefined for a different reason than these up here. These were undefined because there was no number that would work. And this is undefined because every number will work. Every number will work here, so it doesn't make sense to say that 0 divided by 0 is 0, because it could just as well be 8 or -5 or whatever. Okay, so again, so what was the correct answer? What should we say this is?
It's undefined.
Undefined, not 0. How should we have known that from the start? Because you can't divide by 0. You're not allowed to divide by 0. It's okay to have this 0 on the top of the fraction, but we're not allowed to have this 0 on the bottom of the fraction. So, okay, good. Now, again, this is still not indeterminate. Indeterminate is a new idea in calculus that we'll be getting to in our next session. This is just undefined. And let me try one or two other things here. Do you know how to simplify this? Try this on your screen if you know how to simplify this.
A divided by B divided by C. A divided by B divided by C is really just this equals A over 1 times C over B. Okay.
That's good so far. That's an excellent step. So what you're remembering is that the way to divide by a fraction is to multiply by its reciprocal. Excellent. But we can simplify some more now.
AC over B.
Okay, good. Would you agree that's certainly simpler than what we started with, right?
Mm-hmm.
Notice, why is this much better than what we started with? Because we started with a fraction inside of a fraction. Very confusing to have a fraction inside of a fraction. So our AC over B is much better because it's only a single fraction. Okay, that's excellent. Good. So a lot of people don't remember how to deal with those complex fractions, but that was the correct approach. Good. So let me also... So you can try this one on your screen as well. Let's simplify this.
Like that?
Okay, good. That's right. Didn't sound 100% confident, but you worked that out correctly. Excellent. I'll go back to my screen. So the one thing that might be giving you a little difficulty here is you should remember that the way you divide fractions is by multiplying by the reciprocal of the bottom fraction. The one thing that might be confusing you here is that the thing on the top is a fraction and the thing on the bottom doesn't look like a fraction. But how could I rewrite the bottom so it's a fraction too?
You could rewrite C as C over 1.
That's right. And that's really what you ended up doing. That's how you know how to find the reciprocal. Once you write it like this, you know the reciprocal is 1 over C. You kind of did that on this problem too. How could we rewrite the top here so that the top is also its own little fraction?
You can rewrite A as A over 1.
And that's what you actually did when you worked it out. You did this as A over 1 times the next thing. So anyway, when one thing is a fraction and the other thing isn't, it might actually help to make both of them into fractions so it's easier for you to take the reciprocal. All right, so let's try this example.
B, C. Okay, so this is just A over B times D over C. AD over BC.
Okay, good. In a way, that one, I'll go back to my screen. That was kind of easier because they were both fractions to start with. But we're just using the idea that you divide by a fraction by multiplying by its reciprocal. I'll write down another problem. Let's try this.
A over 1 Okay.
Okay, good. That was right. I'll go back to my screen. So, would it be legal here to cancel the A's?
No.
You can tell that wouldn't work because that wouldn't give us the right answer, right?
Right.
Did the A's end up canceling?
No.
No, but I wanted to warn you against that because that's what I see a lot of students want to do here. A lot of students want to think that they can cancel the A's, but when you actually work it out more carefully, the A's, this A is not being divided by this A. When you look at it more carefully, this A is being multiplied by this A. This looks like the A's are dividing into each other, but when you work it out more carefully, you can see they're really multiplying each other. All right, so I just wanted to warn you against that because that's a mistake I see people make oftentimes. So that's why it's important not to take shortcuts on these problems. Don't take shortcuts. Instead, do what we've just been doing here and rewrite it out by multiplying by the reciprocal. Because when people try to do this in their head, they tend to make mistakes. So this is what we could call, we've been working with complex fractions. A complex fraction is when you have a fraction inside of a fraction. And what we've learned here is a method that we can use to simplify the complex fractions so that there's only one fraction. And the basic approach is to treat it like a division and multiply the fraction on top by the reciprocal of the fraction on the bottom. Okay, so that's a little bit of the algebra and arithmetic that we'll need for this the next section that's coming up. And now we're ready. Now we'd be ready to go into the calculus for that section. That looks like that's our time for today. Let's try this problem. You can try this on your screen if you want, or you can tell me in words how you would do this. How would you attack this?
Okay. The limit as x approaches to x plus 4. So...
Go ahead and do this on your screen.
Okay. This is really bad, but I sort of forget how to handle limits right now.
Okay, so that's a good reason for us to go back and review those. So it's been a while since we went over these limits. So I'll give you some help with this. So the technique that you went over for limits in the earlier chapter was called the direct substitution method. And the direct substitution method is, let's go back to my screen. The direct substitution method works like this. To evaluate what this limit is, what the limit of x plus 4 is as x approaches 2, the direct substitution simply substitute 2 in for x. So I'm going to substitute 2 in for x. And I got 6. So that's the answer. The answer turns out to be 6. So this is the direct substitution method.
Okay.
This is the method you covered earlier in the course. One thing that I think will be a good notation for us to use today is that when you use the direct substitution method, I think it's good to put a question mark above the equal sign, because the direct substitution method doesn't always work. It's something that you test, and then you see whether it works. So when we first substituted in 2 for x here, we weren't sure whether this was going to work or not. It all depends on whether the right-hand side simplifies nicely or not. In this case, the right-hand side simplified nicely to a number, so then I took away the question mark because it turned out that this method really did work. So your textbook doesn't use this notation, but I think this is good for our understanding to remember when you first apply the direct substitution method to a limit, you're not sure whether it's going to work or not. So we're not really sure whether these are equal yet. That's what this question mark shows. You only know that they're equal when you are able to simplify the right-hand side down to a single number that makes sense. Okay, so it turns out that anytime you have a continuous function, you can just use this direct substitution method. When you have a continuous function, you can use the direct substitution method. How do you know whether the function is continuous? Well, you're not supposed to worry about that too much in this class. The great majority of the functions that you're given in the class are usually continuous. The majority of the functions are usually continuous unless there's an obvious reason to think otherwise. Certainly, polynomials are generally going to polynomials are continuous. So this is kind of a normal-looking function. So like most of the normal-looking functions in the class, it's going to be continuous, and therefore the direct substitution method is going to work on that problem.
Okay.
Okay, so that's a review of the earlier method that we used for finding limits. So let's try this problem on your screen. Try to attack this using a similar method to what we were just talking about.
Okay.
Okay, good. So the method you used there was the direct substitution method. You put a question mark over your first equal sign because at first we're not sure whether direct substitution will work or not, but then at the end you had just a regular equal sign because it really did turn out to give us the correct answer. Okay, very good. So that was right. So we would start by plugging in this. And I'm going to be a little persnickety here and say, for beginners, it's better not to string a bunch of equations in a row. It's better to just write one equation at a time. This last problem was super easy, so maybe in this case it was okay. But going forward, it's better for beginners to write each equation separately. Just people make fewer mistakes that way, unless the problem is super easy, which kind of this problem was. Okay, so anyway, that was a good application of the direct substitution method for this problem. Very good. Now, what does this mean? How would we read this aloud? Would you read this line aloud?
The limit as x approaches 3 from both sides is 4.
The limit of what?
F.
Let's see. Now that the f wasn't really quite mentioned in this problem, so f is not really defined. The best way to read this is the limit of x squared minus 5 as x approaches 3 is 4. And that's probably what you were thinking. So the best way to read this is the limit of x squared minus 5 as x approaches 3 is 4.
Okay.
The limit of x squared minus 5 as x approaches 3 is 4. So to review, what would be a good way to read this aloud?
The limit of x squared minus 5 as x approaches 3 is 4.
Good. And how would you read this aloud?
The limit as x, the limit of x plus 4 as x approaches 2 is 6.
Okay, good. Okay, well, you can try this problem on your screen.
So we have a problem here, I think. I think we have to solve this a different way.
Can you think of any other ways to solve this?
Not right now.
Okay. Now, this is something that we could approach using some of the algebra that we talked about yesterday. Before you use the direct substitution technique, it's a good idea to simplify the function. Is there any way to simplify x to the 6th divided by x squared?
Yep.
That's really something we should have done before applying direct substitution. It's always a good idea to simplify first before we apply direct substitution.
Okay. So when you divide, you subtract. Okay.
So what's the answer?
0.
Okay, good. So that second solution was a good way to solve this. I'm going to go back to my screen. Let's work out a better notation for attacking that. So
the first time I got the answer as undefined, so I'm kind of confused.
Okay, yeah. Now, technically, your first answer wasn't quite undefined. Your first approach here was you tried to apply direct substitution to this expression. And when you did that, you got 0 over 0. But when you get a 0 over 0, when you're using the direct substitution method to compute a limit, that is not considered undefined anymore. That's a new term that you and I haven't talked about. It's indeterminate.
Okay.
When do we use this term indeterminate? Indeterminate is used when the 0 over 0 occurs when you're using the direct substitution method for finding limits. When you're using the direct substitution method for finding limits, that's when we use this term indeterminate. And maybe it's not that great of a term, because it doesn't mean that it's impossible to determine the limit. It just means that this particular approach wasn't able to determine the limit. So all that we got here, that's why I like using this question mark, by the way. So it turned out here that this question mark was well warranted because this turned out not to be a good way to figure out the limit. This method of figuring out the limit was not able to determine the answer. So then we simply had to go back to square one and apply a different method. So when you get 0 divided by 0 as part of using the direct when you're using the direct substitution method for finding a limit, that is no longer considered undefined. It's now considered indeterminate.
Okay.
And what that means, that doesn't mean it's impossible to determine the limit, but it does mean that that particular method is not going to determine the limit, and you have to go back and try to find a different method. So let's go back and look at a different method here. So the alternative approach that we had to use here was to simplify the expression first. So x to the 6th divided by x squared is x to the 4th. By the way, how is this different from what you wrote down? Well, notice that I can't get rid of this limit term here yet. I haven't applied direct substitution here yet, so I can't just write this is x to the 4th. We're still trying to find the limit as x approaches 0 of x to the 4th. And then for the next line, now that I've simplified this, now I can apply the direct substitution approach. Now I can substitute 0 into this expression. And 0 to the 4th is 0. So I think this would be the best notation for this problem.
So on those last two lines, did you mean to put x to the 4th?
Which two lines? Oh, these here? Well,
yeah.
No, because what we're doing here is, remember, what was the question asking us for? The question was wasn't asking us for the limit of x to the 4th. It was asking us for the limit as x approaches 0 of x to the 6th divided by x squared. So I'm purposely, each equation, I'm purposely rewriting the left-hand side down again. I don't want to lose that because that's my goal. My goal in this whole problem is to figure out the limit as x approaches 0 of x to the 6th divided by x squared. So I don't want to rearrange the left-hand side of the equation. What I'm doing is rearranging the right-hand side of the equation. So I took this right-hand side, the limit is of x to the fourth as x approaches 0, and by applying the direct substitution method, I plugged in I turned that into 0 to the fourth. So yeah, I think this is the best notation for this approach, to just keep rewriting what you're trying to figure out on the left-hand side, and your work for figuring it out goes on the right-hand side of each equation.
Okay.
Okay. All right. So, and in fact, it would probably be better not to have written this first line at all. Before we try, so the point here is before you apply direct substitution, it's good to simplify the expression. Before you apply direct substitution, it's good to simplify the expression when you can. But if you did apply direct substitution here, you would get the outcome that was indeterminate, meaning that you were not ready to apply direct substitution yet, and you had to go back and try a different approach. Notice that we still ended up using direct substitution. We used direct substitution, but we directly substituted into x to the fourth rather than x to the sixth over x squared. Okay, so this is how we can apply some of the algebra that you and I talked about yesterday. Does this problem make sense now?
Yep.
All right, and I do think this would be a good notation for attacking these types of problems. So how would we read this line aloud?
The limit of x to the sixth divided by x squared as x approaches 0 is 0.
So it shows that we've answered the question. Okay. Let's try this problem. Let's try this on your screen.
Okay. So. Okay.
Okay. So what's the answer?
0.
Okay. I noticed that in your top line you wrote 0 divided by 0 equals 0.
Right. Oh, no, that's not right.
Okay, that's right. And so if you're going to apply direct substitution there, it comes out indeterminate. Maybe it would be better not to even bother with the direct substitution there and just go straight to the second line and simplify first. But if you're going to apply direct substitution there, it comes out to be equal to 0. All right, I'm going to go back to my screen again. I'm just going to write out what I think would be a slightly better notation for that problem.
Yeah, I'm still kind of confused on how to set it up, I guess.
So I'm not even going to bother with direct substitution yet. Instead, I'm going to start by simplifying this expression.
So when do you write it on the right and then write it below? That's what I'm confused about.
Well, I think all the problems that we've done today, we've basically done using this same approach. so in all of these problems, we're trying to solve for a particular limit. So I just keep rewriting that limit on the left-hand side of the equation to remind myself that that's what I'm trying to solve for. For example, here we were trying to solve for the limit as x approaches 2 of x plus 4, so I just wrote that on the left-hand side of each equation. Or here we were trying to find the limit as x approaches 3 of x squared minus 5, so that's the expression I wrote on the left-hand side of each equation. Or here we were trying to find the limit of x over 6 divided by x squared as x approaches 0, so that's what we wrote on the left-hand side of each equation. So we just keep rewriting the left-hand side, and then the right-hand side we want to keep rewriting in simpler and simpler forms. So the first thing we could do to simplify this right-hand side is say that x to the 7th divided by x third is x to the 4th. And I'm still going to put the limit here because I haven't taken the limit of that expression yet. Now I need to simplify this right-hand side some more. How can I simplify the right-hand side some more? Well, I can simplify it some more by now applying direct substitution. And now since I'm applying direct substitution, I'm going to put in this question mark to show that I'm not sure whether this is going to work. I didn't put a question mark in here because this was not direct substitution. This was pretty much guaranteed to be correct. X to the 7th divided by x to the 3rd is certainly x to the 4th. Here's the step that's not guaranteed to work where we're using direct substitution. So that's where I put in the question mark. By the way, maybe this is confusing. That's a different question mark than I used here. Maybe instead of doing it like this, I should say, the problem is to find this limit. So I'm not using the question marks in two different ways. Okay, and now I can simplify the right-hand side again. 0 to the 4th is 0. And now I can get rid of the question mark over the equal sign because it turned out the direct substitution worked here. The right-hand side really did simplify into a single number, so we really have figured out what the limit is. So you might want to take a few seconds to study the notation that I used here, because as the problems get more difficult, I think this will be the best way to write these things out.
Okay. Okay.
Okay, and as we practice it, we'll get more comfortable with it. So how would you read this line aloud?
The limit of x to the 7th power divided by x to the 3rd power as x approaches 0 is 0.
Okay, good. Let's try this one.
Okay.
So what's the answer?
-8.
Okay, and I noticed that you solved this problem 2 different ways. So did you solve it 2 different ways for practice, or was it necessary? After you got your first answer, was it necessary to try the other method, or could we have just stopped?
I just wanted to make sure that I did it correctly.
Okay, good. So was it necessary? In this case, no. So basically you did the direct substitution method twice. The direct substitution method worked fine the first time, so it wasn't necessary to try it the second way, but that also confirmed our answer. I would say, though, that it seems like it would be easier on these type of problems simply to simplify the x to the 5th over x squared from the beginning, rather than substituting in. So it would probably have been better in this case just to simplify from the beginning rather than substituting in. But you did get the same answer in both cases here. Okay, good. I'm going to go back to my screen. I'm just going to show again how I would kind of notate this problem, because we're still not quite notating this in the way that I think is going to be most useful to us as we go along. You did get the right answer there, so I'll just show you what I think would be a better notation for this. Okay, well obviously I basically did the same things that you did, but I think that this notation will help us to avoid mistakes as we go forward. So I think it's a good idea to really, right now we're really just at the beginner stage, so we shouldn't be trying for shortcuts. We should be writing out the full notation for each line, like this. So I think this is the best way to write out the full notation for each line without taking any shortcuts. This is the best way to avoid mistakes as we move on to the harder problems. So I use the same method as you, but here's the notation that I think that is safer for these types of problems. In a problem like this, there's really no need to, there's no point plugging in the -2 until we've simplified the expression. Even though we could, it's still going to be easier to simplify the expression first. So that's what I did in this first line. So I want you to, again, take a few seconds to study how I notated this until you feel that you understand where I got those lines from.
Okay.
Okay, how would you read this line aloud?
The limit of x to the 5th divided by x squared as x approaches -2 is -8.
Okay, good. Okay, so you did get that question right. I just wanted to polish off our notation a little bit. Let's try this problem.
Okay.
So what's the answer?
0.
Okay, that's the right answer. That's the correct answer here, and we figured that out using the direct substitution method. I'll go back to my screen.
Was that the right notation?
I'll be picky and make some slight suggestions on that, but it was getting better. You used the right method there. So what I would start, so first of all, I would say the first thing we should ask is there a way to simplify this expression? And the answer is no. There is no way to simplify this expression, so then we can go straight into direct substitution. So I'll put a question mark on this line to show that we're not sure the direct substitution is going to work yet. And again, I'm going to try to avoid ever working horizontally because that leads people to make mistakes. I'm going to write out a new separate equation for each line. Well, what's 0 squared divided by 5? It's 0. So now I can get rid of the question mark because the direct substitution method turned out to work. It's simplified to a single number. This is pretty close to what you wrote down. I think this is just a slightly better way to write it out. So direct substitution worked here. So in this case, so what's the method here? The method is first ask if you can simplify the expression, and then use direct substitution. First, simplify the expression, and then use direct substitution. If you can't simplify the expression, then go directly to direct substitution. Okay, so how would you read this aloud?
The limit of x squared divided by 5 as x approaches 0 is 0.
Good. Now, what does that mean? What does that mean? What's the difference? So what that means is when x is close to 0, x squared divided by 5 is also close to 0. That's the meaning of a limit. Limits tell you about what the expression is like when the input is close to this number. So again, this means when x is close to 0, x squared divided by 5 is also close to 0. The limit is not about what happens when x equals 0. It's about what happens when x is close to 0. Maybe as we go along, that'll become clearer. Okay, let's try this problem.
Yeah, I'm still confused on the notation. Like, I'm not sure when I plug 0 into x. Like, should I bring this?
So the first thing we should ask is, first we ask ourselves, is there any way to algebraically simplify the expression? Is there any way to algebraically simplify the expression x cubed divided by 2x plus 3, or is it already as simple as we can make it?
It's already simplified?
That's right. So what other methods do we have for figuring out limits? The only other method we have for limits is direct substitution. So now we're going to do a direct substitution step. So I think it's a good idea for direct substitution. And you can do that on the same line that you were just working on, because you haven't finished that equation yet. We don't want to leave that line until we finish that equation. Since we're using direct substitution, we can put a question mark over the equal sign to show this is just a test. We're not sure that this is going to work yet. And then we can plug in the 0. And maybe we should write off to the side here that we just use direct substitution. Direct substitution is kind of a weird or unusual method. It's different from some of the other math that people have learned. So maybe it's good to always make a note when we've tried this direct substitution step. Okay, and now we're going to continue trying to solve for the limit. We should just keep rewriting the left-hand side because that shows what it is we're trying to figure out. And then on the right-hand side, we should keep trying to simplify the right-hand side as much as possible.
Okay.
Okay, good. Let's also put a question mark on the on this next to last equal sign. At that point, we still weren't sure whether direct substitution was going to work or not. Then at the end, it turned out that it did work because we were able to simplify to a single answer there at the bottom. As we go along, it'll be clearer why this is the correct way to go. This topic's a little bit tricky because it's a little bit hard to see why things make sense until we've seen a few more examples. But anyway, that's the right way to attack this problem. Okay, so how would you read that last line aloud?
The limit of x cubed divided by 2x plus 3 as x approaches 0 is 0.
Okay, that's correct. That's correct. Okay, so I'm going to go back to my screen. So let's try this problem.
Okay.
Okay, how did you determine the sign of 0?
I plug it into my calculator.
That sounds good to me. That works for me. Okay, good. So that gave us our answer. Good. Okay, very good. So I'll go back to my screen. So the first thing we need to ask ourselves is there any way to simplify this expression, sine x? And there really isn't. So then we go straight into the direct substitution method. This is a point where it would be a good idea to put in the question mark and to label that we're not sure whether this is going to work here yet or not. And now we can see it did work because it simplified to a single number. Okay, so how would you, so this is basically the notation that you used. I think it would be good at this point to put in this question mark to show we weren't sure whether direct substitution would work. And maybe we should get in the habit of labeling when we try the direct substitution approach. As we go, we'll see how this is useful. We have to do a few examples before all the significance here is going to be seen. We have to kind of build this up. How would you read this line aloud?
The limit of sine of x as x approaches 0 is 0.
Great. What does that mean? Well, what this means is when x is close to 0, the sine of x is also close to 0. That's what this means. It's kind of a weird idea. It's kind of a fuzzy idea for mathematics. But what it means is that when x is close to 0, the sine of x is close to 0.
So is sine of x the function f?
Well, in a sense, well, first of all, there is no function. We never mentioned f here. If you want to call it f, you can. You can say I'm going to call sine of x the function f. But these problems haven't introduced any particular name function f. You could say this is the function we're taking the limit of. You could say this is the function we're taking the limit of. And in the previous problem, x squared plus 5 was the function we were taking the limit of. And in the previous problem, x to the 7th divided by x cubed was the function we were taking the limit of. You can call that function f if you want to, but if you wanted to, you could call it g, or you could call it bob, or you could call it whatever you want. It's true that usually in calculus we call functions f. So I guess if you could say the function that we're taking the limit of is the sine of x, and the most common name for functions in calculus is f. But there really isn't any need to really think of it in those terms. There really isn't any need to call this f to get these particular problems right. We can just call it sine of x.
Okay.
Let's try this problem.
Okay.
Okay.
Right.
How did you figure out the cosine of 0?
My calculator.
That works for me. Okay, very good. All right, so that's a good approach for this problem. So how would you read that last line?
The limit of cosine of x as x approaches 0 is 1.
Great. What does that mean? Well, what it means is when x is close to 0, cosine x is close to 1. It means that when x is close to 0, cosine x is close to 1. For example, what would be the cosine of 0.0000001? Well, it would probably be pretty close to 1. That's what this is saying. When x is close to 0, the cosine of x is close to 1. Okay, that was the right method for attacking that problem. So that's the type of limit we'll be needing in this section. That was a good approach, and that was good notation.
So it can't be 1. So I see that x is approaching some number, but then the function that we're interested in, it should be defined, shouldn't it?
So it is true. So there's two different things that you could say on this last problem. So what does this mean? This means that when x is close to 0, cosine x is close to 1. And what does this mean? Well, this is a little hard to write out, but and what does this mean? This means that when x equals 0, cosine x equals 1. So those are both true, but they're slightly different things. This says that when x equals 0, cosine x equals 1. I had to make up this function f here to express this. This means when x is close to 0, cosine x is close to 1. So in this case, those are both the same. Maybe it would be clear to see the distinction between them if we went back to this problem here. So what does this mean? This means that when x is close to 0, x to the 6th divided by x squared is close to 0.
Okay. I mean, I guess it's not that big of a deal. I'm just trying to wrap my head around it because it seems like if you set something equal to 0, it is 0. But I guess that's not true.
Let's see. Well, let me finish this example here. So what this means is that when x is close to 0, x to the 6th divided by x squared is also close to 0.
Okay.
However, what happens when x equals 0? When x equals 0, what is x to the 6th divided by x squared?
Zero.
When x equals 0, what is x to the 6th divided by x squared? Looks like you're having trouble with that, but I would say it would be undefined. Because you can't divide by 0?
Right. Well,
so this is a case where the two functions are two different things. So this function here the function is undefined when x is equal to 0. I think you're saying, why can't you just simplify this to call it x to the 4th? Well, the problem is that works when you're trying. That works when you're trying to figure out what the function is close to 0. But you can't. This function, the function is not x to the 4th. The function is x to the 6th divided by x squared. Those are not always equal. They're only equal when x is not equal to 0. As long as x is not equal to 0, these are the same thing. But if x was equal to 0, these would be two different functions, because this is a function that's defined at x equals 0, and this is a function that's not defined there. But I can see I'm probably just confusing you here. So these ideas are pretty subtle. To actually have like a full understanding of limits is actually a pretty hard job. It's a pretty hard, subtle concept. I'm I guess I'm trying to get through this a little bit on the cheap without explaining everything. Okay. So I guess I have to admit, I haven't fully explained exactly what these limits mean here, because we don't need that to get the problems right in this section. To have a really full understanding of limits, that would take quite a bit of time right there, and it's not really necessary to get the problems right in this section. I think that as we move through the problems, we'll be able to get a better feel for what the limits mean. This is something that I think you have to get a feel for as you go. You kind of have to accept at first that some things might seem a little pointless or might not quite make sense. But it's probably not the best use of our time right now for me to try to explain more carefully exactly what these limits mean, because it really is a pretty hard idea, and it would take more time than it's worth for the problems in this section. So what I just said here probably didn't make too much sense to you. So I'm not going to try to pour more time into that. Instead, we'll just keep moving forward, and I think as we go, we'll get a better feel for what this means. Okay. Okay. But yeah, you shouldn't be surprised that this is somewhat confusing because the concept of a limit is a very difficult and subtle concept. It's one of the big reasons why college math is more difficult than high school math. The good news is, again, we don't need to have too deep of an understanding to get the problems right in this section. Okay, so in any case, what does this mean? This means that when x is close to 0, the cosine of x is close to 1. It's also true that when x is equal to 0, the cosine of x is equal to 1, but that's a separate idea from the limit. And as we go, maybe we'll get a clearer idea of what that means. All right, but in any case, let's keep going forward because we want to get to the point where we can solve the questions in this section. So let's try this problem.
Okay.
Okay, what was your answer?
1.
Great, very good. How did you evaluate e to the 0?
With my calculator.
Sounds fine. Okay. So how would you read that last line?
The limit of e to x as x approaches 0 is 1.
Excellent, good. Now what does that mean? What it means is when x is close to 0, e to the x is close to 1. Now, it's also true that when x equals 0, e to the x equals 1. But that would be a separate idea. Limits are about what happens when x is close to 0. So this tells us when x is close to 0, e to the x is close to 1. Okay, so that's a good approach for that problem. I'm going to go back to my screen. What's this?
One.
Right. What's this?
1.
Good. What's this?
1.
What's this?
1.
What's this?
1.
So I did want to point out, this is a problem where it's not necessary to use the calculator. There's nothing wrong with using the calculator to check, though. But it is good to know that anything to the 0th power is 1. Anything to the 0th power is 1. And if we knew that, we could evaluate this without the calculator. But it's perfectly okay to use the calculator as well. Okay, good. All right. So this one I'm going to do on my screen. Do you have this written down?
Mm-hmm.
So let's try to attack this. Here's the limit we're trying to figure out. Well, our general approach here is, first we should ask, is there any way to simplify this expression? But there doesn't seem to be any obvious way to simplify it. So we go to our normal method of direct substitution. So I'll put in a question mark because I'm not sure the direct substitution will work. What am I going to substitute in for x?
1.
Okay, so do you see how I got this line?
Mm-hmm.
All right, so then we're ready for the next line. Okay, well, what is the natural log of 1?
0.
Okay, sounds like you did that on your calculator. That sounds good to me. So that top becomes 0. And what goes on the bottom?
0.
That's right. Now, if you got 0 divided by 0, normally if you got 0 divided by 0 when you were doing a problem, you would say undefined. But that's not what you do when you get it in the middle of direct substitution. So maybe I should have written I was doing direct substitution because that changes the game. When you get a 0 divided by 0 while you're doing direct substitution, that's not considered undefined anymore. It's considered indeterminate. And what does that mean? What does it mean that it's indeterminate? It means that we can't use direct substitution to figure out this limit. At least not yet. That doesn't mean there's no way to find the limit. It just means that we can't use direct substitution yet to figure out the limit. We have to go back to square one and try again. So here I've gone back to square one. I'm going to try again to see if there's any other way to figure out this limit. Well, it would be nice if there was some way I could simplify this fraction, but there really isn't any way to simplify this. So here's where we have to use the new calculus from this section of the textbook. So the new calculus here is that there's a trick. When direct substitution gives you an indeterminate form, there's a trick. The trick is take the derivative of the top and the bottom of the fraction. This is just a trick that just happens to work. So in this class we don't do any proof, so I'm not going to prove why this works. But the trick here is that when you get an indeterminate form, you can just take the derivative of the top and the bottom of the fraction and then try to evaluate the new limit. So that's what I'm going to do here. And so what we're using here is what's called L'Hopital's rule. It looks like La Hospital, but it's pronounced L'Hopital's. Okay. So L'Hopital says, to use L'Hopital's trick, we're going to take the derivative of the top and the bottom of the fraction. So here's the standard derivative notation that we've used many times before.
So it's not the derivative of the interesting function.
That's an excellent point. That's right. We're not taking, so that's a very good thing that you pointed out there. We're not doing this. Good point. We're not taking the derivative of the original function. L'Hopital didn't say that would help us. We're not taking the derivative of the original function. We're taking the derivative of the top and the bottom of the fraction separately. So I should have pointed that out. That's a good thing that you noticed that. Okay, that's right. Well, on the left-hand side, I'm just going to keep rewriting the original limit to remind myself that that's what I'm trying to figure out. And now I'm going to try to rewrite this left-hand side. Well, how could I rewrite the top of this fraction?
1 over x.
Excellent. And how could I rewrite the bottom of the fraction?
1.
That's right. What do you think we should do now?
Now we can try our first technique, which was direct substitution.
Okay, you could do that, and that would work. I think there's a better thing to do now, though, because what's the other technique we've talked about? Simplifying the expression before you do direct substitution. I think we've seen in our previous examples, it's generally a good idea to simplify the expression before you do direct substitution. So what does this simplify to?
Okay, that's 1 over x times 1 over 1, which is just 1 over x. I mean, I guess you could see that because it's dividing something by 1. It's just going to be what it is. But yeah, okay.
Okay, so everything you just said was exactly right. Everything you just said was exactly right. The full technical way to do this would be to use the algebra, the arithmetic we went over yesterday, and multiply by the reciprocal of the denominator. But the second thing you said was right too. Anything divided by 1, dividing by 1 doesn't change the top of the fraction. So if you wanted to, you could just go straight from here to here. So we can either write this line or go straight from here to here, whichever you feel more comfortable with. Okay, so it's always a good idea before you do direct substitution to simplify the expression. It's always a good idea before direct substitution to simplify the expression. Unfortunately, there was no way to simplify this expression, but this expression could be simplified. That was one of the advantages of using L'Hopital's rule. It gave us a new expression that was easier to work with. Notice how helpful L'Hopital was here. L'Hopital completely got rid of the log. By using L'Hopital, we were able to get rid of the log and give ourselves a simpler expression. Okay, now we can do the direct substitution technique. What should I substitute in for x?
1.
Right. And I'll make a note that, again, I'm trying direct substitution. Maybe now it's clearer why I thought it might be a good idea to use these question marks. Because notice, sometimes direct substitution doesn't work. When we tried direct substitution the first time, it didn't actually work. It came out indeterminate. So I thought it might be a good idea to use these question marks to show that this is just a try. We're going to have to see whether this actually works or not. It didn't work the first time. Well, this time I think it worked, because this time we did not end up with an indeterminate form on the right-hand side. This time we were able to simplify until we got a 1. And now we're done. What's the answer to the question?
1.
Yeah. So how would you read this line?
The limit of the natural log of x divided by x minus 1 as x approaches 1 is 1.
Okay, that's right. Good. Okay, so this is what the main questions in this section are like, using L'Hopital's rule here. So this would be a good problem to go back and review to see how we did this. All right, so to go back to the beginning, here was the original limit. First you ask, is there any way to simplify this expression algebraically? And the answer is no, so we tried direct substitution. But when we tried direct substitution, we got 0 divided by 0, which is an indeterminate form. Remember, what does it mean when you get indeterminate form, 0 divided by 0 when you're doing direct substitution? It doesn't mean there's no way to find the answer. It doesn't mean the limit is undefined. It means you got to try another approach. It means we have to go back to square one and try another approach. So then we went back to the original limit, and we learned the new calculus of this section is L'Hopital's rule. L'Hopital says if direct substitution gives you an indeterminate form, gives you 0 divided by 0, then you can evaluate the limit by taking the derivative of the top and the bottom of the fraction and then trying direct substitution again. So it kind of takes a lot of words to describe L'Hopital's rule, but it's not too hard to see what we actually did here. And as you pointed out, we're not taking the derivative of the whole expression. We're just taking the derivative of the top and the bottom separately. I think this is a good notation for writing down the first step in L'Hopital's rule. A good notation for the first step is to write out that we're taking these derivatives like this. So this would be a good notation for you to use when you're doing these problems. So as usual, I'm trying to write out the notation that I think is most helpful for these problems. Then we used a little calculus. It's good that you remember the derivative of natural log was 1 over x. Before we try direct substitution, it's always a good idea to simplify the expression if you can. So we did this. Notice that I don't get rid of this limit. I don't stop writing limit until I've done direct substitution. Once I do direct substitution, I stop writing limit on the right-hand side. But until I've done direct substitution, I keep writing that limit phrase on the right-hand side. That's really the best way to write this out. Then once I've tried direct substitution, I stop writing limit on the right-hand side. So that's the pattern here. I haven't done direct substitution yet, so I still write lim. I haven't done direct substitution yet, so I still write lim. I haven't done direct substitution yet, so I still write lim. I haven't done direct substitution yet, so I still write lim. Now I'm doing direct substitution, so it doesn't really make sense anymore to keep writing lim on the right side of the equation. And then that simplified, and we got our answer. Okay, so this is the method that we use when we get an indeterminate form of 0 divided by 0. Okay, does that make any sense?
Mm-hmm.
Okay, good. One moment. Okay, so here's another problem. And again, I'll work this out on my screen. So here's the limit that we're trying to figure out. Okay, so what do we do first? Maybe this isn't the best example. All right, I don't like this example. Let me try something else. Okay, so we'll try this example on my screen. Well, the first thing we should ask is there a way to simplify this expression? But there really is no way to simplify this. So the next thing to try is direct substitution. What should I substitute in for x?
1.
So what do I get on the top of the fraction?
0.
And on the bottom?
0.
Now, if this was an ordinary problem, we would say this is undefined. But remember, we don't use that term when we're doing direct substitution. When we're doing direct substitution, we use the term indeterminate. And what does indeterminate mean? Indeterminate means that this method is not going to work, and we have to go back to square one and use a different approach.
What's a normal problem? Is that a limit problem as well?
I didn't quite understand the question. You asked me what was a normal problem?
Right. Yeah, you said that.
Oh, well, suppose you were doing this.
Okay.
How would you evaluate this? Well, you would plug in, oh, not 0, 1. How would you evaluate this? Well, you would do this. You would get this. And then you would say, oh, f of 1 is undefined.
Okay.
This is what I meant by kind of a quote-unquote normal problem. Normally, when you're doing math and you get 0 divided by 0, you say that what you were trying to solve for was undefined. This function is not defined at x equals 1. So that's kind of what I meant by a more normal problem. But when you get 0 divided by 0, when you're using the direct substitution method for a limit, we don't consider that undefined anymore. We call that indeterminate, because there might still be, the limit might be defined, we just have to solve it a different way. So this means there's no way to figure out f of 1. F of 1 just doesn't exist. But this doesn't mean that the limit doesn't exist. It just means we have to try a different approach. That's why we need a different term. The limit's not undefined here. We just haven't been able to determine it yet. Okay, so what's our other approach? Well, it's what we just learned. We learned that when you get this indeterminate form of 0 divided by 0, you should switch to L'Hopital's rule. And L'Hopital says that the trick is take the derivative of the top and the bottom of the fraction in the limit. So we're not going to explain why this works. It's just a trick that happens to work. So what should I write on the top of this fraction?
Just write 8x to the 7th power.
Great. And what do I write on the bottom of the fraction?
5x to the 4th.
That's right. What can I do now?
We can try direct substitution.
That's right. You could do that now. However, let's try to get in the habit of asking if we can simplify the expression before we do direct substitution. So is this an expression that we can simplify?
It is.
Yeah. What does it simplify to? Take your time.
8/5 x cubed.
So here you're using what we went over yesterday, subtracting the exponents. Since I have not done direct substitution yet, I'm going to keep writing lim on the right-hand side. Until we do direct substitution, I have to keep writing lim on the right-hand side. Now would be a good time to use direct substitution, because now there's no way to simplify this further.
Okay.
You could have done direct substitution here as well, but I think it's better to be in the habit of simplifying when you can. What are we going to substitute in for x?
1.
And I'll put in the question mark because we've seen that direct substitution doesn't always work. And what does the left-hand side simplify to?
Just 8/5.
Well, it turned out that direct substitution did work here, so I don't need the question mark anymore. And what's the answer to the question?
The limit as x approaches 1 is 8/5.
Yeah, the limit of x to the 8th minus 1 over x to the 5th minus 1 as x approaches 1 is 8/5. Very good.
Right.
Okay, so that's another example of how to do the problems in this section, another example of L'Hopital's rule. Okay, so let's try to summarize this. When does L'Hopital's rule apply? Let me write that down over here. So far, this is the only time that we've learned that you can use L'Hopital's rule. It doesn't always apply. It only applies if you've tried direct substitution on a limit and gotten 0 divided by 0. L'Hopital's rule only applies so far when you've tried direct substitution on a limit and gotten 0 divided by 0. Later on, we'll see other situations where it applies, but so far, this is the only one we've seen. You have that written down?
Mm-hmm.
So, for example, would L'Hopital's rule apply to this limit? Well, no, because when we did direct substitution, we did not get an indeterminate form. So you could not use L'Hopital's rule here. You might think you can't use L'Hopital's rule because it's not a fraction, but that could be solved easily. You could make it into a fraction, but you still cannot use L'Hopital's rule here because we did not get an indeterminate form by direct substitution. Could we use L'Hopital's rule here? Well, no, because we didn't get an indeterminate form by direct substitution. Could we use L'Hopital's rule on this problem? I don't know if you remember this problem, but could we use L'Hopital's rule here? Well, yeah, if you remember, we did get an indeterminate form on this problem. So we could have used L'Hopital's rule. But we didn't because there was a better way. On this problem, there was a better way, which was simplifying the expression. Notice that even when L'Hopital's rule applies, it's not necessarily the fastest approach. Here, L'Hopital's rule would apply because we did get an indeterminate form, but it was that there was a better way than L'Hopital's rule, which was just to simplify the expression. X to the 6th divided by x squared was x to the 4th. Does L'Hopital's rule apply to this limit? Well, no, because when we tried direct substitution, we got -8, not 0 divided by 0.
Okay.
Okay. Here's an interesting one. Did L'Hopital's rule apply here? Well, no, because when we tried direct substitution, we got 0 divided by 5. So notice, this is indeterminate.
Mm-hmm.
Is this indeterminate? No.
No.
Is this indeterminate? No. Only this. It's got to be 0 divided by 0. This is what we said earlier was kind of undefined for a normal problem. But it's only when you get 0 on top and 0 on the bottom that you can use L'Hopital's rule. If there's only a 0 on the bottom, you can't use L'Hopital's rule. And if there's only a 0 on the top, you can't use L'Hopital's rule. And you don't need it, because you could just simplify that to 0. So far, the only time we've seen that L'Hopital's rule applies is when you have a 0, when direct substitution gives you a 0 on the top and on the bottom. So by the way, if you don't get 0 divided by 0, you cannot just go in willy-nilly and take the derivative of the top and the bottom of the fraction. If you don't get 0 divided by 0, L'Hopital's rule can give you the wrong answer. You can only take the derivative of the top and the bottom of the fraction if you've already tried direct substitution and you got 0 divided by 0. That's the only time when it's guaranteed to work to take the derivative of the top and the bottom of the fraction. If you just take the derivative of the top and the bottom of any old fraction for any old limit, it could easily give you the wrong answer. So we can only apply L'Hopital's rule to a particular case. So notice, on these problems that I did, this first step was totally necessary. Before you do L'Hopital's rule, you have to try direct substitution on the original function. Before you try L'Hopital's rule, you have to try direct substitution on the original function. Your instructor does kind of have trick questions where he tries to trick people into using L'Hopital's rule when it doesn't really apply. And the only way to avoid those traps is to always try direct substitution on the original expression first.
Okay.
Same on this example. Before I could do L'Hopital's rule, I had to try direct substitution on the original expression. Only once you've gotten 0 divided by 0 are you justified in using L'Hopital's rule. So that's an important aspect of that. Okay.
So, I guess you have to try direct substitution before you simplify? Or does it not matter?
Actually, something that we've been trying to learn today is it's better to simplify before you do direct substitution. It's better to simplify before you do direct substitution. That's different from what I was talking about. I was saying you have to do direct substitution before you apply L'Hopital's rule. You have to do direct substitution before you can apply L'Hopital's rule. But simplification is a different idea. It's better to simplify before you do direct substitution. For example, we saw that on this example here. Before directly substituting, it would be better just to simplify this to x to the 4th and then substitute in. Or we also saw that on this example. before substituting in x equals 1 here, it was better to simplify this to 1 over x, and then we could do direct substitution. So maybe that's something that's given us some trouble, so I'll write that down. This is not a requirement. It's not mandatory to simplify first, but it'll make our life much easier and make us less likely to make mistakes. Okay. Tell me when you have that in your notes.
Yep.
All right. Okay, well, I've done a couple of demonstration problems on my screen, so now it's time to, for us to try this on your screen. So try this problem, and try to use the same approach and notation that we've just been demonstrating for the last few problems.
Okay.
Good. Good.
messed up.
Okay, let me give you a little help with that notation. So when does it make sense to stop writing down LIM? When you do direct substitution, that's when you can stop writing down LIM. So yeah, that line where your cursor is now, you haven't done direct substitution yet, so we should still write the LIM notation there. And then the next line, you still haven't done direct substitution, so it still makes sense to write the LIM notation. Now the next line, you still haven't done direct substitution. You're just simplifying. So we should still write the LIM notation. Good. Now the next line, I think you did apply direct substitution, so that's when you can drop the LIM. So this is a little hard. I can see how this is a little confusing because, again, we haven't really had time to really get a feel for exactly what limits mean. So some of these rules might seem a little bit arbitrary, but it's still best to use the best notation here. So the idea here is we should keep writing the LIM in every line until you apply direct substitution. And then when you're applying direct substitution, it doesn't make sense to write that LIM notation anymore.
Okay. I like chain rule much better than this. These limits. I don't know.
Well, hopefully as we go forward, we'll get more comfortable with it. But it is a difficult concept, and like I say, it is a difficult concept, and we're not really taking the time to explain exactly what these mean. So there's a point where we are kind of going to be just following some rules, maybe without totally understanding why they work. But I do feel that as we do more examples, we'll get a better feel for it.
Oh, okay. Yeah, the limit of x to the 9th power plus 1 over x cubed plus 1 as x approaches -1 is 3.
That's right. Okay, so we ended up with the right answer here, and we went back and fixed our notation. How did we know that we could use L'Hopital's rule here? We knew because when we tried direct substitution, we got an indeterminate form. So then we used L'Hopital's rule, and we ended up using some good notation on this problem. Okay, that's good. Let's go back to my screen. So why don't you take your calculator out, and let's put this function in on the calculator. The original function before we applied L'Hopital's rule. Okay, so tell me when you have that function entered in.
Okay.
Good. All right, so now let's, I'll go to Zoom Standard to get back my standard window because I don't know what my Zoom was before. Okay, so you got a graph that looks like this?
Mm-hmm.
All right, now let's see what happens. What do we care about here? Remember, we want to know what will this expression be like when x is close to -1? We want to know what will this expression be like when this x is close to negative 1. So let's try trace, and let's see what happens when x is equal to negative 1.
Nothing.
What does this mean, nothing here? Why is it giving us nothing? Well, you already know why, because remember, you already know this expression is undefined when x is negative 1, right? Because you get 0 divided by 0. The function x to the 9th plus 1 over x cubed plus 1, that function is undefined. So notice that this is telling us that the function is undefined at that point. All right, so let's do this. Let's go back to trace. And now, instead of plugging in negative 1, I'm going to plug in a number that's close to negative 1. Like this. Because remember, that's what limits are really about. The limit is about what this expression is like when x is close to negative 1. So what do you get when you do that?
Something really close to 3.
What do you know? In fact, on my calculator, I got exactly 3, even though that's just rounding off here. Anyway, so what we're going over here is, here's how you can check your answers on the calculator. You can use your calculator to check these limits by using this approach. You can graph the function, and then you can put in a number that's really close to where you're taking the limit, and then that will give you a good sense of whether your limit actually came out to be correct or not. So we found here that when x is very, very close to negative 1, the function really is going to be close to 3. So that's the way we can check our answer on the calculator. Okay. Maybe let's, maybe I'll see what happens if I zoom in on that a little bit. So the calculator doesn't actually show this, but so this is kind of what the graph really looks like. You can't, the calculator can't show gaps, but this is what the graph really looks like. At x equals negative 1, this function is undefined. There's a gap. The function doesn't equal anything when x equals negative 1. But when x is close to negative 1, the function is very close to 3. I'm hoping this will give you a slightly better feel for what limits mean. So the function here is undefined when x equals 1, but the limit still exists. The limit tells you what the function is like when x is close to negative 1. When x is close to negative 1, the function is close to 3. Okay, fair enough. As we go, maybe we'll get a slightly better feel for what those limits mean. But anyway, you did that problem correctly. That's good. So let me write down another problem. Let's try this problem on your screen again using the same approach. These problems take some space, so make sure you have enough space to complete the problem.
Okay.
Good. You're applying direct substitution, so we don't keep writing the LIM notation. That's good. Let's write our step a little bit more. What is the sign of 0?
0.
So let's write that down. And what do you have on the bottom of the fraction? And then to the side, you can write that that's indeterminate. We don't know we have an indeterminate form until we get a 0 on the top and a 0 on the bottom. Okay, but that's good. 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 We haven't practiced those derivatives for a while, so it's good that you remember the derivative for the trig function. What did you just write on the top of the fraction there? Okay, good. So now you're using direct substitution again, so you dropped the LIM. That's good.
Okay, so the limit of sine of x over x as x approaches 0 is 1.
Okay, outstanding. Very good. Let's go back to my screen. Okay, so let's try that again, and now let's check that on the calculator. So we go to the y equals menu, and what are we going to type in for y equals?
Sine of x divided by x.
Right, I changed my zoom, so I'm going to go back to standard. All right, it might be a good idea for this picture here to zoom in a little bit so we can get a better look. Now we want to try to use the calculator to evaluate this limit. So we could go trace, and we could try putting in x equals 0. So give that a shot. What happens when you trace at x equals 0?
Y is undefined.
That's right, as we already knew. You already saw that that gave you 0 divided by 0. The calculator really should show a little open circle here, but it doesn't have the software to do that. Okay, good. So how can we use the calculator to confirm this limit? What could we plug in instead of 0?
0.00001.
Yeah, just a number that's very close to 0. And what do you get when you do that?
1.
That's right. Technically, the calculator got something close to 1 and then rounded it off. But anyway, did this confirm our answer?
Yep.
Okay, so again, we can use the calculator to confirm the answers for these types of problems. And so just to show you again, the graph here really looks like this. This function is not defined at x equals 0, but when x is close to 0, the function is close to 1. Hopefully, again, that'll give you a better feel for what limits mean. Okay, good. So that was a good method for that problem. Notice that I think this is the first problem we've done today that involved trig functions. That didn't really make any difference. Once you understand L'Hopital's rule, you can apply it to anything, whether it's a trig function or not. Okay, good. Okay, let's try this problem. So again, make sure you have enough space to try this on your screen. Okay, good. So that's a good application of the derivative there. It would be easy to make a mistake with the signs, but you got the sign correct there. That's good. So you can see maybe it gets a little bit tedious to keep rewriting that left-hand side each time. So let me give you a shortcut. Go ahead and erase what you have there on the left-hand side now. And if you want, why don't you just make a ditto mark on the left-hand side, since we just keep writing the same thing over and over. All right.
Like that?
That's fine with me, yeah.
Okay.
Just saves us a little bit of time, but it reminds us that the left-hand side still represents the same thing as before.
Okay, so the limit of 1 minus cosine of x over x squared plus 2x as x approaches 0 is 0.
Okay, that looks good to me. So let's go back to my screen, and let's check that on the calculator. So you can talk me through how you would do that.
Okay, so y equals parentheses 1 minus cosine of x divided by x squared plus 2x. And graph that. And if I trace over to 0, I should get undefined. Yep, that's true. So 0.0001 is 0.
Okay, yeah, so when I put in 0, it doesn't give anything for y, and then you put in 0.000001, and what did your calculator give you?
0.
Right. Again, that's really only an approximation. It's not exactly 0, but they have rounded it off to 0. Does that confirm our answer?
Mm-hmm.
Okay, good. Okay, very good. So again, we can always check our answers for these on the calculator. Very good. All right, that was a good process for that problem. So we're making some progress with this. Let me write this down. All right, here's another problem. Let's give this one a shot.
squared. 0 over.
Okay, let's talk about this one a little bit. So you did something I didn't think of on this problem. You had a good idea, which is that we've talked about in the past that before you do direct substitution, you should try to simplify the expression. I didn't think about that here, so that's good that you had that thought. Before you did direct substitution here, you tried to see whether you could simplify. So the first thing you did is that you factored the bottom of the fraction. That was excellent, but then you didn't follow through. Because the whole purpose of factoring would be to see whether you can simplify. So what is it? Was there any way to simplify that original expression?
Right, we could cancel out the top and bottom.
That's right. That's the whole point of factoring. The whole point of factoring is to do that canceling. So you did a good job with the factoring, but then I think you didn't take the next step. So before you did direct substitution, we should have done that extra simplification step. So let's erase the last few lines and try to simplify before we substitute. You might have exhausted its memory. Yeah. We'll have to break out the old eraser. We should erase that last line because remember the idea is before you do direct substitution, you should try to simplify.
Okay.
Okay, good. And since you haven't done direct substitution yet, it was good that you kept writing the LIM notation. Okay.
So curious as to why I got a different answer, even though I didn't simplify it further. Okay.
Okay. You said something about how you were wondering why you got a different answer. I'm not sure what you meant by that.
Right. So before, I plugged 2 into here. I got 0 over 0.
That's right, which was indeterminate. Right. So notice that's not really a different answer. What that means is if you do direct substitution before simplifying, you can't determine any answer. So you have to try a different approach. And you did try a different approach. Your different approach was simplify first and then try direct substitution. And when you did it that way, you got a 1. So in a way, they weren't really different answers. Remember, indeterminate is not an answer. Indeterminate just means that that particular method didn't succeed in getting any answer. Try again. When you get 0 divided by 0, what that's saying is try something else. Well, you did try something else. What you tried here was simplifying before you substituted. And that did the trick. When you simplified before you substituted, you did not get an indeterminate form anymore. That's the whole reason to factor. Notice if you're not gonna cancel the x minus 2's, there's not really any reason to factor the bottom. The whole point of factoring the bottom is that gives us a chance then to cancel out those x minus 2's. Okay, now the way you were going to do it would have gotten you the right answer. If you don't simplify, you have an indeterminate form. So L'Hopital's rule does apply there, and it should give you the right answer. That might be a good homework problem to see that you would get the same answer either way. But this is when you can avoid L'Hopital's rule. I guess it's better too. This is a little bit simpler approach. Is that making sense?
Yep.
Okay. Well, we can go back to my screen, and let's check your answer.
At x equals 2, y is not defined.
Good. Which we already kind of knew. Good.
For the 1.99999. Y is close to 1, which is what we got, I think. Let me check. Yep.
Okay, good. All right, so we ended up with a answer here again. So what the function again looks like there, whoops. The function is not defined at x equals 2, but when x is close to 2, the function is close to 1. That's what the calculator is basically telling us here. Okay, so on this last problem, we saw that even on problems where L'Hopital's rule could be used, it's not always necessary. So this was a problem where if you don't cancel, L'Hopital's rule applies, and you could use it and get the answer. You could do that as a homework problem. But it's always better before you do direct substitution to simplify. And if you do that, you saw that then L'Hopital's rule wasn't used. So just to review, I think this is an important idea that we've been talking about today, if I can find it. It's best to simplify the expression, if possible, before trying direct substitution. It's a good habit to always try to simplify the expression before trying direct substitution, if possible. If it's not possible to simplify, then you can't, but it's always good to try that out. Okay, good. I hadn't even thought about factoring on this problem, so that was a good instinct, but then we have to follow through with the next step and actually...
So if you didn't factor, then... it's not simplified. It wouldn't be simplified. So, trying to think about what you would do if you didn't factor. If you didn't factor, then you could just direct substitute right into it and get 0 over 0. So then, I guess, if you thought that was simplified, then you would just try L'Hopital's rule, and then you would solve it like that.
Yeah, that sounds right. So the only problem with what you said is I'm not clear if you just want to be clear. That's exactly what we've been doing with all of these problems. So for example, let's look at the previous problem. So here's the problem that we did a moment ago. This problem didn't simplify, right? There was no way to simplify it. So when we used direct substitution, we got 0 divided by 0, and then we applied L'Hopital's rule. Or maybe here's an example that might be more interesting. Here's an example that's more similar. This is also a polynomial, but this one doesn't simplify. So here we had no choice but to just use direct substitution. And when we did that, we got 0 divided by 0, which is an indeterminate form. So that justified us in then going on to use L'Hopital's rule. Okay. So I think that's what you were saying. So I think what you were saying was correct. Let's try this problem. That last problem that we did would be a good one to mark and go back and try again, because we did have an issue with that one.
Well, that was pointless, basically, I think. So.
Oh, I think we ended up miscopying the problem here. Take another look at my screen. Sorry, I should have caught that.
X squared minus 4. Okay. Sorry. Okay, I think this is right.
So what's the answer?
0.
So do we need L'Hopital's rule here?
We don't.
No. Or if we wanted to, could we use could we be allowed to use L'Hopital's rule to check our answer?
Well,
Could we also do this using L'Hopital's rule just to check if we got the right answer? So I'm not asking you to actually do L'Hopital's rule. I'm asking, does L'Hopital's rule apply here?
it doesn't.
How do you know? When does L'Hopital's rule apply?
When you have 0 over 0.
That's right. Only if you do direct substitution and get 0 over 0. Only if you get that indeterminate form. So not only do you not need L'Hopital's rule would be wrong on this problem. So this problem is a trap. So I've been taking all these problems from the website. All these problems have been from the website. This is a trap problem on the website because most students get into a bad habit where they just automatically go straight to L'Hopital's rule without checking direct substitution in the original expression. And you can see why that doesn't work. Unless you do direct substitution on the original expression, you can't tell whether L'Hopital's rule is even legal or not. So that's why we've been having to, you have to get that 0 divided by 0 before you're justified in using L'Hopital's rule. So that this is a good example of why that's important. Let's go back to my screen. And that's also why we had to go over how to do ordinary limits. So that last problem was really just an ordinary limit like you learned how to do in an earlier chapter. That last problem was just an ordinary limit like you learned how to do in an earlier chapter. That's why we had to start the session by reviewing how to do ordinary limits, because there's still going to be some of those scattered among all the other problems. Okay, so let's finish off by checking that answer on our calculator.
I get a different.
You didn't get the same answer? Did we make a mistake?
X squared minus 4 divided by x squared plus x minus 6. Weird. Well,
So are you looking at my screen? Does your graph look like this?
Mm-hmm.
Yep. All right, so then you hit trace, and what did you plug in for your trace? X equals what?
1 second, I'm sorry.
Yeah, take your time.
I traced the 2. It should be undefined. Huh. Yeah, it's strange. I have a different graph than you, but I get the same answer. Strange.
You're saying your graph doesn't look like this?
No, it doesn't.
Okay, let's go back to the y equals. Maybe you left out a parenthesis here or something? Compared to what you have written down to what I have written down here.
No, it's exactly the same.
And you went to Zoom standard?
Yep. Oh, I guess maybe it's similar. It has some extra lines in it for some reason. Okay, but okay, yeah.
The graphs really should be exactly the same. I'm not sure whether they're coming out differently. But anyway, what number did you plug in to trace? X equals what? What number were you tracing?
-2.
Great. And what happened when you did that? What did you get?
Y is 0.
Excellent. Notice it didn't say undefined, did it?
No, it didn't.
And that shouldn't have surprised us because we know this function isn't undefined at x equals -2, right?
Mm-hmm.
Remember, that was the whole point. You didn't get any division by 0 on this problem. You didn't get any division by 0. The function was not undefined there. So we don't even have to bother plugging in a number that's close to -2. Anyway,
okay.
so you got so when you plugged in x equals -2, what y value did you get?
0.
And what was your answer previously?
0.
Okay, so anyway, that confirms that that answer came out correctly. Okay, so anyway, that's our time. So anyway, so we've learned how to do basically one type of L'Hopital's rule question. So one thing is I can see, so these limits can be a little bit difficult because again, we haven't quite talked about exactly what limits are from a philosophical standpoint because that would just kind of take too long. But I think once we started getting in the rhythm, I think we were getting a good rhythm for doing these types of L'Hopital's rule problems. This section has a bunch of other types of problems. So far we've learned how to do one of the types of problems for L'Hopital's rule. L'Hopital's rule applies to 2 or 3 other types of questions that we haven't gotten to yet. But anyway, we've seen how to apply it to one type of problem. So I thought we made progress on that. Okay, so that's our time. Okay, well, let's try working out this problem on your screen. Okay.
So much paper for calculus. I've already used almost 2 notebooks so far. So just for calculus.
Yeah, right. Well, it's better not to. This is not a good place to conserve paper. It's better to use as much as you need. The only problem is when people have too many notes, things get lost, and it can be hard to review. So it's kind of thing where you have to make an effort to boil things down. Okay, so it looks like since we've gotten, we used L'Hopital's rule, and we got an indeterminate form, so it looks like you decided to use L'Hopital's rule a second time. That's something that that's something you and I haven't ever seen before, but you might have already seen that on your own. So that seems like a good approach. If L'Hopital's rule doesn't work the first time, you can use, and you get an indeterminate form, you can use it a second time. Now, notation-wise, we should keep writing the LIM notation until we've tried direct substitution. So only when we do the direct substitution does it make sense to stop writing the LIM notation. The important thing of what you just wrote down is that you're taking the limit as x goes to 0. If you leave that out, you can't see any reason why you substituted in 0 in the next line. So once you substitute in the 0, then we can stop writing the LIM, because now we've used the direct substitution. So now that we're using L'Hopital's rule a second time, again, we should keep writing the LIM until we tried the direct substitution.
Okay.
I think there was a mistake. Let's scroll up some. What went wrong here? Scroll up some more. Ah, yes. Okay. So point to the line that says, there you go. Okay, you found it. Good.
Oh, boy. Okay. So,
So the first time wasn't really affected. We still get an indeterminate form. So we can still apply L'Hopital's rule again. But now we're taking a derivative of a different thing, and that'll affect our outcome.
the second derivative, we get 6x. We get root of cosine is negative sine x minus 0.
So there's something got left out of that denominator. Good. Okay, I don't think you've made any mistakes so far.
Okay. So this is 0. Okay, I've got to go a third time.
If at first you don't succeed.
Derivative of sine is cosine, so negative cosine. Oh, right there.
Good. So now you're doing direct substitution. So that previous line, we should still be writing the LIM notation. Because otherwise, it doesn't make sense that we plugged in x equals 0 in the next line, because that had dropped out. Okay?
Oh, do this down here. Okay, so limit is x approaches 0. X cubed sine of x minus x
Good.
equals 6 over 4. limit x approaches 0.
Now, at this point, you've done the direct substitution, so now we don't have to keep writing the LIM anymore.
Okay.
So the basic idea here is you should keep writing the LIM until you've done the direct substitution. And then when you're doing the direct substitution, we don't need to write the LIM anymore. How did you get that 1 on the bottom of the fraction?
Cosine of 0, so -1.
Yeah, cosine of 0 is 1, but then they have that negative sign. Okay.
All right.
All right. So now the basic idea here is something we hadn't talked about before, but you'd already picked up on it, which is if you use L'Hopital's rule and you get another indeterminate form, you can use L'Hopital's rule again. And in fact, you can keep using L'Hopital's rule as many times as you like, as long as you keep getting indeterminate forms. This problem is not really very unusual. It's pretty common to have to use L'Hopital's rule more than once. So this is an important extension of what we went over yesterday. We made a few careless mistakes on this, but overall, I think you understood conceptually how to attack this. Let's go back to my screen. And we can check it on the calculator. You can check it on your calculator too.
Y equals x cubed divided by sine of x minus x. Trace to 0. Y is indeterminate, so trace
Undefined there. Yeah.
undefined.
Because the calculator is not graphing the limit, it's graphing the actual function. The function is undefined there. The limit was indeterminate. Okay, so what do you do when we get that x0 is undefined? What do you plug in for x then?
Something really close to 0 in this case, so
Right.
0.0000001. And y...
Looks like, so I put in something that was so close to 0, the calculator got confused and thought it was still undefined. So I'll have to do something that's maybe a little less close to 0.
Yeah, 0.001, it's really close to -6. So that's
So
good.
close to negative, yeah, so very close to what we got, which was -6. So that's strong confirmation that we had gotten that problem correct. Okay, very good. So again, there were some careless mistakes there and some notation problems, but overall conceptually you understood how to do that. So that's an extension of what we went over yesterday. Sometimes you have to use L'Hopital's rule more than once. Okay, good. So I think we made some good progress on this type of L'Hopital's rule problem, but there's some other types that we need to make sure we understand how to do. So let's talk about this. You know what this is?
Oh, this is as x approaches in positive infinity, x equals infinity.
The limit is infinity. That's right. You and I haven't talked about this much. Now, this is one way that limits are different than ordinary problems. In ordinary math, infinity is not a number or a symbol that we use. We don't normally treat infinity like a number, but it turns out that it's helpful to kind of treat infinity as if it was a number when you're working with limits. So we will say that this limit really is infinite.
Mm-hmm.
What's this?
The same, really, really, really big.
So the answer would be infinity again. Good.
Infinity,
now,
yep.
Here's how we might work this out. We can do a kind of direct substitution here. Again, infinity is not a real number, but when you're doing direct substitution for limits, you can treat it as if it was a number. So here I'm doing direct substitution. Since the rules are different when you do direct substitution, maybe it helps to write down when we're doing that. Now, if we treated infinity as if it was a number, what would be infinity cubed?
Still be infinity.
That's right. Huge number cubed is still huge, and that just confirms what you had said a moment ago. So your first answer was correct. But sometimes it can be helpful to treat this as if it was direct substitution and actually plug in and see that we really are getting infinity here. Okay, good. What do you think this is?
Oh, this is also infinity.
That's right. Now, again, we can show that a little bit more clearly if we do direct substitution, and I'll plug in infinity for x. When you do direct substitution, you can treat infinity as if it were a number. Well, what would e to the infinite power be?
E to the infinite power is just it's I think it's just e to infinity, or is it just infinity? I think it's the same thing.
We don't. It wouldn't help us too much to write the same exact thing. We want to try to simplify that. So the idea here is if you take a huge exponent and raise e to that huge exponent, you get a huge answer. Mm-hmm. So I'm just confirming the answer you gave me a moment ago, that this limit really is infinity. But on some of the problems we go through, it'll be useful to have these types of techniques. What does this really mean? What this means is we can make e to the x as big as we like by making x big enough. This just means that if you make x big enough, you can make e to the x as big as you like. Okay, so so those are a couple of limits that will be useful to us. Let's take out your calculator again, and let's focus on the function natural log of x. Let's look at what that function looks like. So let's go to the y equals menu and put in natural log of x.
Okay.
And then graph it.
It's approaching something.
And let's see. What can we notice about this? First of all, notice the function is not defined for negative x's, right?
Right.
Notice there's no function for negative x's. You can confirm that by plugging in, say, -1, and notice that it's undefined there. So let's go back and change the window to start at 0, since we're not going to need the negative x's. And we'll graph that again. Okay, good. So first of all, what can we learn from this? What is the limit as x goes to infinity of the natural log of x?
We can use our calculator. Well,
what does the graph make it seem like the limit is? As x goes to infinity, what seems to be happening to the natural log of x?
It's going to infinity.
Yeah, it kind of seems like that. It seems like it's getting bigger and bigger, right?
Mm-hmm.
It's a little hard to see because it's happening very slowly. But you could go trace and then hold down this right key. And notice that it'll take you off the screen. And notice that as we continue to move further out, the function just seems to keep getting bigger and bigger, although very slowly. It keeps getting bigger, but it gets bigger at a very slow pace. It turns out that the limit really is infinity. It's a little hard to tell from this whether it's approaching an asymptote or going to infinity, but it really is going to infinity. But one interesting thing about logarithms, notice logarithms increase very slowly. It's interesting to notice that logarithms increase very slowly. Okay, I'm going to go back to zoom standard to get back my original zoom. And let's see what happens if we really focus on what happens around the origin here. So let's move to around the origin and then zoom in so that we can see what happens as, what do you think? So based on this, let's try to figure out what might be the limit as x approaches 0 of the log of x.
As x approaches, well,
what does the graph make it seem like the limit is here?
The limit is going to be 0.
So you're saying the y-coordinates here are getting closer and closer to 0?
No, the y-coordinates are getting closer to...
We could try tracing it out.
Negative infinity.
Yeah, you can kind of see it's going down to negative infinity, right? But try tracing. I'll go to the trace here. Is that working for me? Maybe not. Trace x equals, say, 1. That puts me here. What happens when I try tracing down? It doesn't update the graph, unfortunately. All right, so much for that idea. That idea didn't work. All right, but anyway, you can kind of see that it's going down towards negative infinity, not towards 0. Basically, this is the y-axis here is a vertical asymptote. It turns out that it's approaching that asymptote quite slowly, but it is approaching that asymptote. Okay, so here's two limits that aren't really necessarily obvious. You can kind of figure them out on the calculator like we just did, but you can probably just memorize these. We've never really talked about what natural logarithms mean, so we can't really explain why these make sense, but we can see from the graph that these are the correct limits. So these are worth memorizing. So what happens to the natural log of x as x goes to infinity?
Natural log of x approaches infinity. The natural log of x is approaching infinity.
Yeah, it also goes to infinity, although very slowly. And what happens to the log of x, natural log of x, as x goes to 0?
As x goes to 0, the natural log of x is approaching negative infinity.
Good. Actually, something I should add here is this. Have you ever seen this symbol? Do you know what this means?
Where it has the limit of the natural log of x as x approaches 0 from the right side.
Do you see why we really need that here? Because notice x can't approach 0 from the left side for this function, because the function is undefined to the left of 0, right? So really, to write this down correctly, I have to write it down like this. The limit as x approaches 0 from the right of natural log x is negative infinity. The limit as x approaches 0 from the left is undefined, because the natural log is undefined for those numbers. So what's the natural log of a negative number?
The natural log.
So natural log is undefined for negative numbers. So what's the natural log of a negative number? That would be undefined.
Okay.
And what's the natural log of 0? You can kind of see from the graph that that's undefined too. You could try tracing 0 and see that's also undefined. It never gets to x equals 0. That's the asymptote. So those are some other, so basically the problems we're going to be doing here, some of them are going to deal with natural log, so we need some new facts about natural log. Okay?
Natural log is undefined for negative numbers is 0. Yep, okay, cool.
So what's the limit of actually, everything we wrote down here is actually true for all logarithms, not just natural logarithms. So what's the limit of a logarithm as x approaches infinity?
As x approaches infinity, it's infinity.
And what's the limit of log x as x approaches 0 from the right?
It approaches negative infinity.
Good. And what's the logarithm of a negative number?
It's undefined.
And the log of 0?
Undefined.
Good. So what's this?
Infinity.
And what's this?
0 from the right is negative infinity.
And what's this?
Undefined.
Right. those are all things, if you forgot them during the test, you could actually figure them out using the calculator like we just did, but it would be better to have them memorized. Okay. What's another way to rewrite this?
Okay, so x to the negative a is the same thing as 1 over x to the a.
Like this?
Yep.
Okay, good. So that's a little bit more algebra that we're going to be needing. Do you know what this is?
1 over x. So at the limit of 1 over x as x approaches infinity is 1 over infinity, so that is really just 0.
Good. That's right. Because if you put a huge number on the bottom of a denominator, it gets really close to 0. Again, usually in math we don't treat infinity like a number, but we can treat it like a number for direct substitution for limits. Good. So what would this be?
This is also 0.
Great. You could work it out like this. What's infinity cubed?
Infinity.
And what's 1 divided by infinity?
0, basically.
Yes, that's right. Now that math doesn't work for ordinary math, but those are tricks that we're allowed to use for direct substitution. We can use those tricks for direct substitution. So that just confirms your earlier answer. I'm not saying you have to write out these steps, but on some of the harder problems, it'll be useful to be able to use some of these types of steps. All right, so you gave the correct answer. So how would we work this out?
The limit of x to negative 4 as x approaches infinity is 1 over infinity to the 4th, which is just 1 over, yeah, 1 over x.
So first, I would re-express this, and then I would do the direct substitution. Good.
Okay. So 1 over infinity to the 4th is just 0.
There you go. Okay, good. Let's try this.
E to the negative x is equivalent to 1 over e to the x.
Now we haven't done direct substitution yet, so I'll keep writing the LIM notation. Good.
Okay. And now we can substitute, and so we don't have to write limit. We write 1 over e to infinity, and that is just 0.
There you go.
Limit. Yeah.
What's this?
E to positive infinity, e raised to positive infinity, is just infinity.
Good. So notice e to the x is a totally different beast than e to the negative x. Mm-hmm. There's a huge difference between e to the x and e to the negative x. Both of those come up a lot. Those are pretty important limits, so why don't we confirm that on the calculator. So we can go here, we can plot that we're doing e to the x, and graph it.
X, cool.
I'll go back to Zoom standard because I changed my Zoom. Oh, maybe I was better off with my old Zoom. Okay, so anyway, you can clearly see what's happening to e to the x as x goes to infinity.
As x goes infinity, it's approaching infinity.
You can see the function is going off to infinity, but very quickly. Remember how we talked about how logarithms approach infinity very slowly? Their graph looked like this. Whoops.
Right.
But e to the x is the opposite. It goes to infinity very quickly. So basically, logarithms increase more slowly than polynomials, and exponential functions increase more quickly than polynomials. You might have heard sometimes people talk about something that increases exponentially. What they mean is it increases extremely quickly. And then if I trace to around here and zoom in, it will be easier to see the other limit. And we can see then what's the limit. Oh, no, that's all right. Yeah, I guess that's not relevant. I was going to try to show e to the negative x, but that would be a whole different function. Okay, that's good enough anyway. Good enough.
Okay.
So you could confirm all these in the calculator, but that's good enough. Let's just keep going. All right, so let's try this one.
So we can just go ahead and use we can just use direct substitution and plug in for x. So we have 5 over positive infinity cubed, and that is also just going to be 0.
So this limit is 0 again. Good. That's something you should basically be kind of able to eyeball also. If the denominator gets huge, the fraction will get tiny. Okay, very good. How would you work this out?
This cosine?
Yes.
Okay. As x approaches infinity. Cosine of 0, which is 1.
Great, that's right. So that would be a correct way to work that out. Good. Let's try this one.
Okay. The sine of 8 over infinity is the sine of 0. The sine of 0 is just 0.
Okay, excellent. That's the right way to do that. So when we're doing direct substitution, what would this be?
Doing direct substitution, that is 0.
That's right. And what would this be?
That would be infinity.
Great. If the numerator gets huge, that means the fraction is huge. But if the denominator gets huge, that means the fraction is close to 0. Okay. Now remember, this doesn't work in ordinary math. In ordinary math, you can't. This would just be meaningless. But these are tricks, so we should call these direct substitution tricks. They work. These are tricks that work for direct substitution. Okay. Good. All right. So very good. Now, what about this? What does this mean when you're doing direct substitution? Well, it turns out that this is indeterminate.
Okay.
And you can kind of see why. If the numerator is huge, that would make the fraction huge. But if the denominator is huge, that would make the fraction 0. So it's not really clear who's going to win here. The numerator is trying to make this fraction huge. The denominator is trying to make the fraction close to 0. It's not clear. If there's a tie, that could come out to be maybe 1. Or if the numerator wins, it could go to infinity. Or if the denominator wins, it could go to 0. So this is really indeterminate. Well, what can we do when we get this type of indeterminate form? Well, it turns out that this is another situation where you're allowed to use L'Hopital's rule.
So if we have 0 over 0 or infinity over infinity.
You got it.
Cool.
And these, by the way, could be either positive or negative infinities.
Okay.
They can be either positive or negative. Either way, this is when you can use L'Hopital's rule. I believe these are the only situations when you're allowed to use L'Hopital's rule. There are some other indeterminate forms. There are other indeterminate forms, but they don't allow you to use L'Hopital's rule directly. These are the only indeterminate forms that allow you to directly use L'Hopital's rule. Okay, good. Okay, so let's try working through this on my screen.
Okay. Try direct substitution first. That's the, well, that's 0 up top. We just proved that before. So we have 0 over, oh sorry, yeah, the natural log of infinity of 0 over the cube root of infinity. It's just cube. I think it would just be infinity.
I guess we hadn't talked about that specifically, but you can kind of figure it out. What happens if you take the cube root of a huge number? Well, it's still going to be pretty huge, right?
Mm-hmm.
Okay.
So now that is equal to 0 over 0.
You said this was 0 over 0?
Oh wait, no, that's wrong. 0 divided by some, like 1 billion is really is indeterminate.
You were on the right track. What would happen if you did 0 divided by 1 billion? What would you get?
Zero.
Right. Sounds like maybe you checked that on your calculator. That's fine.
I did.
That's fine. But also, we should just know what happens when you have a really huge... so what happens when the numerator is 0? What does that tend to make the fraction?
0.
Yeah. And what happens when you have a huge denominator? What does that tend to do to the fraction?
Makes it 0.
So notice this is not indeterminate because these are both pulling in the same direction.
Okay.
They're both pulling in the... So what did we get?
0.
Okay. Now, that was a little bit of a digression, though, because we'd made a mistake up here. Where did you get the 0 from? I guess you said the log of infinity is 0?
I was thinking about the natural log of 0, I guess. Wait, let me see. My graph. Y equals natural log of x. So, okay, never mind. It's approaching infinity. So we have infinity over infinity, indeterminate.
It is approaching infinity, although very slowly. We talked about that somewhat earlier in the session. It is approaching infinity here. Okay. So what could we say is the log of infinity?
Infinity.
That's right. So, and this is what we would say is indeterminate. I think it might be tempting to say this is 1, because we have the same thing on the top and the bottom, but infinity is not a normal number, so this actually comes out to be indeterminate, because the numerator is trying to make this fraction really big, but the denominator is trying to make the fraction very small. Okay, so what do we do when we end up with an indeterminate form?
We can use our, I forget how to pronounce it, LH rule.
That's right, so we can use L'Hopital's rule.
L'Hopital.
So we can write that as usual. Like this. I haven't done direct substitution yet, so I'm going to keep writing the LIM. I still haven't done direct substitution, so I'll keep writing the LIM. What's going to go on the top of this fraction?
1 over x.
Good. Do you remember how to take this? We haven't done this type of derivative for a while. Do you remember how to work this out?
I believe that we can rewrite that as x to the 1/3.
Excellent. Now notice we haven't taken the derivative yet.
Right.
So I'll write it like that again.
So now we can rewrite the fraction as 1 over x over 1/3 x minus, 1/3 x to the negative 2/3.
Excellent. Good. So we haven't done that for a while. That's a good thing that you remembered that process. So that's the correct process for taking that derivative. Okay. Now, remember we've talked in the past, before you do direct substitution, you should try to simplify. So we should try to simplify this now. This is a kind of complicated looking fraction. Any ideas of anything we could do to start simplifying this?
Let's see. 1 over x over 1/3 x. I can't see anything.
So you're saying it can't be simplified?
No.
Okay, now there are a few different things we could do here. After all, let's see, there's a couple different ways to approach this. Let me think what the best way to do this is. I'm not sure what the best approach is here, but what's another way to write 1 over x?
1 over x is x to the negative 1.
That's right.
And then okay. So now we could rewrite it as...
Now, I think the best thing to do maybe at this point is, I think we talked about how to divide numbers that have the same base.
Right. So would it be 3x raised to the 3x raised to the...
So what's the calculation we're going to do? So how am I going to figure out this exponent? Well, it's going to be negative 1. What do you do when you're dividing numbers with the same base?
Subtract.
You have to be careful with the signs here.
Mm-hmm.
And I'm just left the 1/3 for later for the time being. So what does that come out to be?
X to the, let's see, negative 1 plus 2/3, so negative 1/3 up top.
You still have a 1/3 on the bottom.
Mm-hmm. So it's 1x up top. So 1 divided by 1/3 is 3. So
Good.
3x is negative 1/3.
You could write that out like this. We talked about how dividing is the same as multiplying by the reciprocal.
Mm-hmm.
Now, I think this would be a difficult limit to figure out by substitution still. How can I rewrite this without a negative exponent?
You can rewrite 1 over 3x to the 1/3.
Like this?
Yep.
Now, the problem is that the x had a negative exponent. The 3 didn't. So you kind of treated it as if it were like this. But the 3 doesn't have that negative exponent. It's just getting multiplied. So it would just be like this. Wow, this is a lot. All right, and then we could simplify that like this. Okay, so I guess there was a lot more tricky algebra here than I had thought about when we started the problem. Well, now what? Now we
Okay.
can try to use direct substitution. Now that I've done direct substitution, I don't have to keep writing LIM. How would this simplify?
0.
Yeah. Again, the fractional, even though this is a fractional exponent, it doesn't matter. A huge number to a fractional exponent is still a huge number. Okay, so after all that work, we ended up with that the answer here would be 0. This is approaching 0. Okay, all right. So that involved quite a bit of stuff. So anyway, let's review the steps here. So here was the original problem. We tried direct substitution, and we got something that was indeterminate. So I guess we had some trouble up front. When we're doing direct substitution, what does this simplify to?
Infinity.
Right. This simplifies to infinity. I think when we did this the first time, we were thinking it was 0. But instead, it's going to infinity. So we got an indeterminate form. So we used L'Hopital's rule. And then we got this fraction here. We were having some trouble simplifying this. There was a couple different things we could have done to simplify this. But here's the approach that we ended up using. So what's another way to write this?
So we rewrite that as x to the -4th.
Now, normally you're probably more used to going from right to left here, but sometimes it could be useful to go from left to right. We had, to make these top and the bottom more comparable to each other, I changed this into x to the -1. And then we can use what we talked about last time. When you're dividing two numbers with the same base, you can subtract the exponents. So there was a lot of practice here with working with negative exponents. This would be a good problem to go back and try again. We had some difficulty with it. But hopefully, ultimately, it made some sense. Okay. Let's try this problem on your screen.
Is that x cubed? I mean squared?
X squared, yes. That's good.
So we tried direct substitution immediately. That didn't work. And then I took the first derivative, and I tried to direct substitute. It's still indeterminate. I took the second derivative, direct substitution. It should be below. I should bring this line below this direct substitution line.
Okay. Yeah, but I guess that's an acceptable shortcut here. These problems are pretty long the way they are, so I saw what you're doing. That's fine. Okay, good. So let's go scroll down to the bottom. So when you're doing direct substitution, what is e to the infinity power?
E to the infinity power is just infinity.
Right. And what's 2 divided by infinity?
0.
Yeah. So you did those steps in your head, and that's fine. I just wanted to make sure those thought steps were clear. So I think that was a good, careful approach. You skipped a couple steps, but that's okay. These problems are long enough the way they are. So I think that was a good, careful approach for the problem. So now let's go back to my screen. And you can take out your calculator, and let's see how to check this on the calculator.
Okay.
So what are we going to type in here for the function?
X squared divided by e to the x.
Good. And I keep changing my zoom, so I'll go back to zoom standard.
Okay. So it looks like as x is approaching infinity, the function is approaching 0.
Does that match your answer?
Yep.
Yeah. I think it'll help here maybe to zoom in a little bit. So I can zoom in around the origin. Now, you can't quite do this the way we did the previous problems. You can't plug in infinity for your trace. But here's something you can do. You can hit trace, and then you just start moving out to the right and see what happens as we go to infinity.
It just keeps getting large, just growing.
It keeps doing what?
Actually, no, it's not. Okay, it gets bigger, and then It gets, and then it starts approaching 0.
Right. Which is what we would hope. Our answer was not that it was going to keep getting bigger, right?
Right.
Our answer, what did we get as our answer for the limit?
0.
Right. Well, at least on my calculator, so if you just hold down the right arrow key, you can get to the point. It'll just keep scrolling off to the side. You can see it's getting closer and closer to 0. Okay. So that's how we can confirm these answers on the trace. You can't plug in infinity, but you can just hold down the right arrow key and keep going out to the right until you're satisfied that it's approaching the limit that you thought was the answer. So these, again, are problems that you can generally confirm on your calculator. Okay. Very good. Okay, so that was a good method. You saw that was a problem where you had to use L'Hopital's rule multiple times. So you just stuck with it and you kept using L'Hopital's rule until you got to a good answer. So that was a good process. Let's try this problem.
I sense chain rule, perhaps. So we take this derivative and chain rule, so this is going to be the derivative. It's going to be 2u times 9, and this is going to be I haven't practiced with you in a while, and I've been watching my instructor, and he does it super shorthand, so I've kind of forgotten our systematic approach for it, but I know it's this times natural, what's the derivative of natural of x is x. So got that. Now we can try direct substitution. So 2 times infinity times 0. So direct substitution, 2 times infinity times 1 over something really big. Yeah, I'm going to do that. Okay. Okay, is this right?
Let's see. It's mostly right until the end. I guess a new issue came up here that I hadn't realized was going to come up on this problem. So you said that infinity times 0 is 0?
Mm-hmm.
Well, it's true that 5 times 0 is 0. But look at those terms separately. So when you multiply by 0, that tends to make the product 0, right?
Right.
But when you multiply by infinity, that tends to make the product what?
Infinity.
So notice how there's a tug of war between those two things. It's not really clear, because remember, that's not really, so the point is one of the terms is approaching 0, and the other term is getting huge. Which one is going to win? Well, it depends which one is moving faster. If the one that's increasing is increasing faster than the one that's going towards 0, the whole thing could be going towards infinity, or there's many different possibilities. So this is an issue that I hadn't expected. We haven't talked about this before. 0 times infinity is another indeterminate form.
Okay.
0, so we should 0 times infinity is another indeterminate form. However, it's not one that lets you use L'Hopital's rule. Remember I said we were done with the indeterminate forms that let you use L'Hopital's rule. So 0 times infinity is indeterminate, but it doesn't let us use L'Hopital's rule directly. In order to use L'Hopital's rule, we have to have a fraction.
Mm-hmm.
Okay, so first of all, let's erase the last thing you wrote down. That infinity times 0 was correct, but the equal 0 was incorrect, because that should really be labeled as indeterminate. So what should we do? Well, we kind of have to try to find a way to use L'Hopital's rule. Whenever you get an indeterminate form, you need to use L'Hopital's rule. But the problem is that L'Hopital's rule only applies to fractions. Well, what we should have done then is moving up a line. There was a way you could have re-expressed your previous line so it was a fraction.
Okay.
You had 2 natural log of x times 1 over x. That could have been re-expressed as a fraction. And that would be make it easier for us to proceed.
So if we see this type of setup,
then we need to re-express our expression as a fraction. I'm sorry, I interrupted you. What were you saying?
Yeah, I think I was just kind of stating that as like a rule set. So like if you have that scenario, then you know you need to go backwards and re-express.
Yes, as a fraction.
Okay, so this is really just okay, so now we can use
Good. So it wasn't that difficult to re-express it as a fraction. Good.
Mm-hmm.
And now you should probably try direct substitution again.
Okay. That's right. So infinity over infinity, it'll be indeterminate, but I'll show that.
Good. And since we're using direct substitution here, we can get rid of the LIM notation in that line.
Yeah.
So now again, we've gotten indeterminate, but this is a more useful indeterminate form because this makes it legal for us to use L'Hopital's rule.
All right, this is the derivative of this. Whole top. So let's see. 2u. 1u. After that, I have to go watch some videos where we work on mechanics of derivatives. Okay. 2. Alright. Now we can try direct substitution. So
okay, so that which I had feared is coming to pass. The connection is getting pretty bad on my end, anyway. We might not be able to continue. But okay. Going back here, it looks like you applied the chain rule.
Mm-hmm.
Any particular reason why you applied the chain rule here?
Because we're taking the derivative of I guess maybe we didn't need to.
So you don't really have any outside and inside functions here.
Okay. Huh.
So I didn't see what you're doing because the screen had frozen up. So you'll have to erase the last few lines and go back up to. You have to again try to take the two original derivatives.
Okay. Okay, so I try to take the derivative at the top. Oh, we need to use product rule. Okay. Gotcha. Yep, product rule. Okay.
Okay. Yeah, I suppose that will work, but that's really overcomplicating things. Why don't I go back to my screen to finish this off, especially because your screen is kind of freezing up on me. Okay, so let's see. Where are we here? We're trying to find the limit as x approaches infinity. And you'd gotten to Is this what you had? Let's see.
I believe so. Yeah. Oh, okay. I just totally messed up. Yeah.
Okay, so I think this is what we had. So anyway, what we actually want to use here, you could use the product rule here, but that's actually unnecessarily complicated. You can use something we talked about. It's been a while since we went over this, but this is what's called the constant multiple rule. The constant multiple rule says that you can simply take a constant that's being multiplied times a function. You can just take that completely outside of the derivative.
Okay. And just a question, why do we have 2 in front of the natural log of x? I'm missing something.
Well, I haven't copied down your whole work, but when you did this the first time, when you were using the chain rule, I think you got the 2 when you used the chain rule.
Okay, so chain rule was used at one point. Okay, gotcha.
That's right. I guess maybe this is getting confusing. This is now our second round of L'Hopital's rule.
Okay.
For the first round of L'Hopital's rule, we really did need the chain rule.
Okay.
But now for this round, we don't. Okay, so are you seeing how I went from this line to this line?
Yep.
So this is the simplification that you could have used here. This is just what's called the constant multiple rule.
Okay. So instead of using product rule.
Yeah. Now, it might be a good homework problem to do this with the product rule, and you should get the same answer, but it really makes it more complicated than it has to be. In fact, you were pretty close to getting the same answer, but this is a simplification we should certainly use. Okay, so now what am I going to write now on the top of this fraction?
So on the top, I'm going to write 2 times 1 over x.
That's right. Now that we've used the constant multiple rule to take the 2 outside of the derivative, we can just use a simple derivative rule. So we don't need the chain rule at this point. There's not really any inside or outside functions. Here, there was an outside and an inside function, but not here. And what happens to the denominator?
The denominator is just 1.
That's right. So what should I write here?
You should write. So now we're going to use direct substitute. Well, we can just rewrite it as 2 times 1 over x.
Did you mean like this?
Yep.
Okay, that's certainly, so before we substitute, we should try to simplify. Well, we can certainly get rid of the 1 in the denominator.
And now we can just leave out the limit, I think. And we can use direct substitution.
Yeah, you could. Why don't we simplify one more time? How can we simplify this?
2x.
Like this?
Yep.
All right, I think we made a mistake there. Remember, how do we multiply 2 fractions times each other?
2 over 1 times 1 over x.
So what would that give us?
2 over x.
Okay. Well, maybe you would have been better off not trying to simplify it, but this is a pretty straightforward simplification here. So now I think would be a good time to use substitution. So what does this come out to be?
0.
Okay, good. I think that is the answer you had gotten earlier, but that earlier method was not reliable. Now we know that this really is 0 here. So this is a problem that gave us some trouble. This is an important one to mark and come back to. This is a problem from the website, so it would be a fair problem on the test. Okay, so we ended up here with our answer of 0. I should write the answer like this. Okay, we can check that on the calculator.
Okay. Y equals natural log of x, close parentheses, squared divided by x.
And since we've been moving around on the graph, you probably want to go back to Zoom Standard. Okay, so did your graph look kind of like this?
It does, yep.
So I think we'll have to zoom in here. We'll want to go to somewhere close to the origin, I guess. And now, how do we check this limit? Well, remember we go to trace, and we just start moving towards infinity and see what happens.
Okay. And it's slowly dipping down towards. It's slowly the function is slowly approaching 0.
So my function at first started increasing.
Right. I just kept going right, and I saw that it starts to dip down. There's a kink.
Come on, dip down.
Right.
Natural log takes a long time to move.
Mm-hmm.
Let's see if I can speed that up here.
It's like at x equals 12.5.
One problem is that you can't just plug in numbers that are not on the graph, so you kind of have to move out to the side.
Yeah.
All right. Well, it does work if you move. Here we go. We're finally moving down again. Okay. So it does turn out that this is eventually going to be approaching 0 here. Okay, good. So that answer turned out to be correct. Okay, this problem gave us some trouble. Let's review some of the steps here. So you tried direct substitution and you found that that gave you an indeterminate form. So then we went to L'Hopital's rule. Okay, and I did want to I think you did use the chain rule correctly the first time, but we got confused the second time. So I did want to remind you what I think is the safest notation for this. So the best approach here is to identify an outside function and an inside function. And it's actually probably easier to start with the inside function. So what's the inside function here?
The inside function is the natural log of x.
That's right. And now, what would be a good way to write the outside function?
U squared.
Okay, so this was the step that you had skipped, that I think you said your instructor tends to skip. I think this is still a good step for us to write out, to explicitly write out the inside and the outside functions that we're dealing with there. It tends to be clearer if you start with the inside function. All right, and then what is the derivative of natural log of x?
1 over x.
And what's the derivative of u squared?
2u.
Remember a few minutes ago you were asking me where did the 2 come from here. This is where the 2 came from when we used this step. And you got this correctly when you did it as well. And the derivative of x, of course, is 1. And now we need to plug in for u. What do we plug in for u?
The inside function, natural log of x.
And I think this takes us to basically what you had figured out there. Okay, so I think this is the notation we were using before. I think this is the safest notation to keep using for the chain rule. You did this correctly, but I think this is a good step not to skip here. So instructors often skip steps because these are so easy for them, but I think it's good for a student the first semester to write it out a little bit more. Okay, and now what went wrong here? Well, you rewrote that like this, getting rid of the denominator, and then you plugged in and you saw this came out to be infinity times 0. And you said, oh, 0 times anything is 0. Well, that doesn't work with infinity. 0 times infinity is indeterminate. Because it's not clear who's going to win, the infinity or the 0. This could either get huge or go to 0 or go to some intermediate number, depending. So what do we do? This is something we hadn't talked about before. What do you do when you get this type of indeterminate form? Well, remember, we can only use L'Hopital's rule when our indeterminate forms are in the form of a fraction. We can only use L'Hopital's rule when our indeterminate forms are in the form of a fraction. So we had to go back and rewrite this in the form of a fraction. And then we were able to proceed, because this then turned into infinity over infinity, and then we could apply L'Hopital's rule to that. And then at this point, that's when we went and took this step. Okay, so there were some new issues on this problem that we hadn't seen here before. Okay, does that make any sense now?
Yep.
All right, like I said, this was a problem from the website, so this would be a good problem to go back and try again to make sure that you were comfortable with it. Okay, so we only did a couple of those x to infinity problems, and we had a little trouble with those, but we're starting to run short on time for the test coming up, so I'm not going to do any more practice on that with you, but those would certainly be good things for you to practice. You should be able to find plenty of practice with that in your textbook, but we're going to have to start picking up the pace a little bit to try to cover more stuff for the test. So let's move on, because there's still another type of problem in this section. So we've covered two different types of L'Hopital's rule problems, but there's still a third type of question that we need to try to get to. I wanted to try to get to that today, so let's move on to this. So let's see, what are our new issues here? What is this?
Control log of x. Substitution 0. I need to graph it. Control log of x. Negative infinity.
Okay. Did you do that on your calculator?
Yeah.
Okay, that's good. That's good that you can use your calculator to help work that out. That's something that you can use during the test. I think it would be a good idea to memorize this, but we just went over this today, so so we haven't got it memorized yet. So it is good that you can use your calculator to work this out again. Ultimately, this would be a good thing to memorize as well, but it's good that you used the calculator and you got the right answer there. Good. How could this be rewritten?
1 over 8 to the 5th.
Good. How could this be rewritten? Oh, okay, that was kind of a weird question. All right, but it could be rewritten like this. Would you agree that this follows the same pattern?
Yeah.
Okay, now this seems kind of weird. This seems simple. Why would we want to complicate it like this? Well, sometimes in math, there can be reasons for complicating things. So normally, when you saw something like this, you just want to leave it like this. But we're going to see now in this section, there's some situations where it's helpful to re-express it. So you can see it's the same pattern, though, as in this case. Okay. So using that same approach, how could this be rewritten?
1 over 8 to the negative 3rd.
Yeah, that seems kind of pointless. It seems like a pointless complication, but we'll see in a few minutes how that's useful in this section. Okay. How could we apply that same pattern to here? How could this be rewritten using the same pattern we applied here?
Right. 1 over 8 to the negative 1.
Excellent. So what I would do first is I would put in, what's the exponent here?
1.
Positive 1. Good. So then we can follow the same pattern and rewrite it like this. Good. Now again, at first this seems like a pointless complication, but if we will soon see how that's helpful for the problems we're talking about. All right.
Okay.
So how could this be rewritten? Now, maybe I won't hold you in suspense. Remember that we just saw that it's useful in this section to be able to write things as fractions, right? We were just seeing that we can't use L'Hopital's rule unless things are written as fractions. That's what was messing us up on the previous problem. We had a product, and L'Hopital's rule doesn't apply to products. It applies to fractions. So these little tricks here are tricks that we're going to try to use to rewrite products as fractions. So here's a product. Can you think of any way we could use the tricks we were just talking about to rewrite this as a fraction?
Yep, so rewrite it as a over, a over, if we had 1 over b, it would be b to the negative 1. So it's 1 over e to the negative 1. A over, sorry, A over 1 over b to the negative 1.
Like this?
Yep.
Okay. I think that didn't quite work out right. Let's try it like this. So how could you rewrite b as a fraction?
B is okay. So
how can you rewrite b as a fraction?
1 over e to the negative 1.
Excellent. So do you see how I went from here to here?
Mm-hmm.
Now I want these to turn into a single fraction. How can I combine these into a single fraction?
A over e.
Like this?
Yeah.
Okay, that isn't quite right. What's the mathematical technique we need to multiply these times each other? How can we multiply these? So, do you know how to multiply these?
X z over yw.
That's right. Good. So, in multiplication, you just multiply the numerators and multiply the denominators. Well, how do you multiply these?
Xz over w.
So what you do is you change x into a fraction. How can we change x into a fraction?
Put it over 1.
That's right. And then you get the answer that you were just mentioning. Okay, good. So that's what we need to apply here. We're really just multiplying fractions here. But how can you change a into a fraction?
Put it over 1.
And then what do we get?
A over b to the negative 1.
Okay, I don't think that was quite what you were saying before. Okay, now notice that doesn't match your earlier answer. Your earlier answer was a over 1 over b to the minus 1. So our first answer turned out to be incorrect. Here's the correct answer. So here's how we can rewrite this as a fraction.
So is there any other way to put b on the bottom when it's a times b? Like if you have a times b, can you just say it's a over... Okay. Yeah, I guess that's what we just did. I don't know what I'm thinking. Okay.
Yeah, I think this is just about the only method that we can use.
Yeah.
Well, I mean, one other way you could write them as a fraction is like this. But that turns out that won't help us with L'Hopital's rule. We need to have a variable on both the top and the bottom. So you could rewrite them as a fraction like this, but that won't help with L'Hopital's rule because we need a fraction with variables on both the top and the bottom. The only way to get a fraction on both the top and the bottom is like this. Or, of course, you could have done something similar and gotten this. If you see what I'm saying?
Right.
Yeah.
So,
but those are the only approaches.
So when we were starting these examples, like we said, a to the negative fifth power equals a over a equals 1 over a to the fifth.
Good.
So if we're looking at the bottom of our fraction in the product, we have b to the negative 1. So it's equivalent to a over 1 over b.
To the positive one.
Right.
Which is different from what you were saying before. You were saying, or maybe I misheard you. I thought you were saying you were going to try to do this.
Yeah, I think that's what I said. I was wrong.
Okay. So I think this was the answer you gave originally. This would be incorrect. But if you were thinking of this, this would have been correct. Yeah, that is correct. Now, so this is another correct answer. But the problem now is we have too many fractions. All right. Okay. Now we have a fraction inside of a fraction. That's too complicated. So so this would also have been a correct answer. But this is now too complicated for L'Hopital's rule. So this is the form that's going to be most useful for L'Hopital's rule, where we simply have one single fraction.
Okay.
Okay, so let's study this process that we used here again to get to the answer here. It's best to do these in little steps at a time. Notice that first I changed b into a fraction. And then by multiplying, I changed the whole thing into a fraction. Okay. And we went over some important algebra here about how to multiply fractions and how to multiply a non-fraction times a fraction. Okay, so let's turn this product into a fraction.
Okay, so we can put p over 1. times 1 over q to the negative 1.
That's a good step.
And then we can so 1 over q to the negative 1 is really just so we have p over q to the negative 1.
Could you say that one more time?
So our answer is p over q to the negative 1.
Okay, good. So that's the same process we used before. Good. You seemed to hesitate a little at the end, but you worked it out.
Mm-hmm.
So that's correct. And now we have a fraction, and we'll see soon that the advantage of that is that it will allow us to use L'Hopital's rule. Okay, good. Let's see.
So we can leave it so if the fraction has a negative exponent on the bottom, we can just leave it like that.
Well, this wouldn't be the end of the problem, but yeah, you could leave it. So this is a true statement. Yeah. Normally, when we had a negative exponent on the bottom, we normally tried to simplify it. But in this case, this is a useful complication.
Okay.
Let's see. One moment.
Okay.
Let's try this one on my screen.
Okay.
Okay, so here's the problem. So the first thing we might try here, as usual, is direct substitution. Oh.
Okay. Yep.
Yeah.
We get infinity times infinity.
Yeah, you sure would, wouldn't you? So what does that mean?
Our answer is infinity.
Yeah.
It's just infinity.
Yeah. All right. That's not indeterminate. So maybe this wasn't the best example I just used here. Okay. Let me see. What was I trying to get here? Okay, well, I was going to try to give you a warm-up for the problem from the website, but I can't think of another warm-up, so I'm just going to throw you into the pool. So here's the problem. No warm-up. Try this problem. See if you can work this out on your screen.
try the substitution first. Zero from the array. We get 0 times infinite.
Good.
Okay, so now use the hopping. We need to rewrite this as a fraction.
That's right. Good.
Rewrite as x plus x.
Now we have to decide, so we're going to use this kind of, this trick we were talking about to turn one of these into a fraction, to put one of these on the denominator. It turns out that things will be much simpler if we put the x in the denominator instead of the natural log x. That's right. So we could apply the -1 trick to the natural log, but that would make that much more complicated. So it's much better to apply the -1 trick to the x.
Okay.
Now, it turns out that if you get that indeterminate form and then you rewrite it like a fraction, you can definitely now use L'Hopital's rule. Well, we can use that as a shortcut. I didn't really quite explain that before. But if you get the 0 times infinity indeterminate form, you can use L'Hopital's rule as long as you rewrite the expression as a fraction.
Okay. Okay, so
now we haven't done any direct substitution, so we should still be writing the LIM in front of each line.
okay, now I can try direct substitution. 1 over 0.
Now this is a very complicated looking fraction. We should definitely try to simplify that before we do direct substitution.
Okay. All right. I'm not sure.
Let's see. So there's a couple different things that you could do at this point. The problem here is that the top of the fraction looks different than the bottom. So you should either try to make the 1 over x look more like the bottom of the fraction, or you should try to make the x to the negative 2 look more like the top of the fraction. Whichever you like should allow us to then simplify. So for example, we could rewrite the top. How could you rewrite 1 over x so it looks more like the bottom, so it's not a fraction anymore?
Oh.
Good. And now that the top and the bottom look more similar, we should be able to simplify. We haven't done substitution yet, so we should keep writing LIM in front of each term.
All right. So
What I was going for here is, remember we've talked about how do you divide two numbers with the same base. What's the algebra rule for dividing two numbers that have the same base?
we subtract
Good. What do we subtract?
the exponents.
There you go. That's right.
Negative 1 minus negative 2, negative 1 plus 2. What's this?
Okay. And we haven't done direct substitution yet, so we should keep writing the LIM notation. Notice that really was a big simplification. It certainly paid off to try to simplify that expression.
Mm-hmm. Okay, I'd stop here.
Yeah, that's a good place to stop. So what's our answer?
0.
Okay, let's move back to my screen. And let's check that on your calculator. You can talk me through what you're doing.
Okay, so now y equals x times natural log of x. I graphed it, and
so probably we should zoom in around the origin,
right,
to see more clearly what's happening. All right, and then what do we do with our trace?
We're approaching 0, so when the function's approaching x is approaching 0, and y is undefined, so we put in 0.001.
Approaching 0 from the right, good.
Right, and we get some really small number, which is 0, close to 0.
Yeah, we got something in scientific notation that's very close to 0. Did that confirm our answer?
Mm-hmm.
Yeah. Notice that we went back to doing limits that are approaching numbers. We had been doing limits approaching infinity for a while, but now we're at a limit that's going to a number again, so we can trace in a particular number here. Okay, so let's see. So there's some things here that I hadn't really explained very well before we moved into this problem. So let me try to be clearer about that now. So when can we use L'Hopital's rule? I didn't quite phrase this as well as I could have. So we can now use L'Hopital's rule. Let's add this to our list. You can also use L'Hopital's rule if you use direct substitution and get 0 times infinity. So this is another indeterminate form. 0 times infinity is another indeterminate form. But in this case, first, you have to rewrite the expression as a fraction. This is kind of a shortcut that's easier than the way I was trying to describe it to you before. So you know it's okay to use L'Hopital's rule if you got 0 times infinity, but before you do that, you have to rewrite the expression as a fraction. Once you rewrite it as a fraction, you don't have to do direct substitution again to prove that you have 0 over 0 or infinity over infinity. You can just trust that that's going to work. So 0 times infinity does make it okay to use L'Hopital's rule if you first rewrite the expression as a fraction. That's kind of what we just did on the last problem. Does that make any sense?
Mm-hmm.
All right. So going back to that problem here. So when we did this, we got 0 times the natural log of 0, which is 0 times negative infinity, which was indeterminate. So we know it's okay to use L'Hopital's rule because we got this indeterminate form. But according to what I just said, the first thing we have to do is rewrite the expression as a fraction. Now, notice the key thing is we're not going to try to put the natural log in the denominator. We should put the x in the denominator because it's simpler. We take this simpler term and put it in the denominator. So we know we could write this. So here's the key step here. How can I rewrite x so it's a fraction?
Oh,
How can I rewrite x so it's a fraction?
X over 1.
That's true. But I need to rewrite x so it's a fraction in the denominator. So that there will be a variable in the denominator. So I just wanted to review the trick we just used on the last problem. Let's just review the trick we just used on the last problem since we had some difficulty with that. How can I rewrite the x so that I have a fraction with a variable in the denominator?
1 over x to the negative 1.
That's right. That was the trick. Now, you could have done that negative 1 trick to the natural log, but that would give us something quite complicated. So this is the better way to do it. I'm just reviewing what we just done in the last problem since we had some difficulty. And now how can we rewrite this as a single fraction?
The natural log of x over x to the negative 1.
Good. And I haven't directly substituted yet, so I keep rewriting LIM. Now, you don't have to do direct substitution now to confirm. You don't need to confirm that we can use L'Hopital's rule. You can just use the shortcut I was just mentioning. Since we got an indeterminate form before, and we've rewritten the expression as a fraction, we can trust that now it's okay to use L'Hopital's rule. So now,
so if you run into a situation where you have something over 0, then you know you messed up, I guess.
Something over 0?
Right, like, so if you subbed in 0, like if you use direct substitution instead of taking the first derivative, then you would get negative and, right, no, you get, I don't know what you would get.
Yeah, so when you tried to substitute, you had made a mistake. So if you were going to do direct substitution here, what you should do first is rewrite. How can we rewrite? This is confusing. How do you rewrite x to the negative 1 so it's so it doesn't have a negative exponent? You can rewrite that as this.
Okay.
If you were actually going to do direct substitution, you'd want to rewrite it like this. And then you'd have natural log of 0 over 1 over 0. And what's the natural log of 0? Well, that's undefined, but as x approaches 0, what does the natural log approach?
Negative infinity.
Good. And what is this? What's 1 over 0? Maybe we haven't really talked about that much. But as this denominator gets very, very small, what's going to happen to this fraction? As this denominator gets very, very small, what's going to happen to the fraction?
It gets bigger.
So it's actually going to infinity, not 0. That was the mistake that you had kind of made the first time. You thought this was going to 0. But as the denominator gets very small, this actually goes to infinity, not 0. That would just confirm that we really can use L'Hopital's rule, right? Because this is an indeterminate form. So this would confirm we could use L'Hopital's rule. So when you tried this on your own, you were getting confused because you thought this was going to 0 when it was really going to infinity. But, you know, maybe I shouldn't have even let us go down this digression, because what I tried to do here is there's really a shortcut so that we don't have to fiddle around with all of this. We got an indeterminate form here. So if we get this indeterminate form and we rewrite the expression as a fraction, we can trust that we can use L'Hopital's rule. We don't need to do direct substitution again. So I don't think we need to spend too much time really practicing these techniques. I think we can use shortcuts to get around that. In fact, I'm going to erase that because I don't think that's really going to be necessary for your test. For the test, I think the best approach is just to stick with what we're doing right here. So again, here's the rule right here. If you use direct substitution and you get 0 times infinity, indeterminate form, you can use L'Hopital's rule, as long as you first rewrite the expression as a fraction. You don't need to do direct substitution again to confirm that you're getting infinity over infinity, even though it is possible to do that, but that wouldn't be worth our time to do that every single time. Those can be confusing. We got 0 times infinity here. We've rewritten it as a fraction, so now we can use L'Hopital's rule. So if you remember, now we're applying L'Hopital's rule here. We're just reviewing what we did on the last problem. So what happens to the numerator?
1 over x.
Right. And what's the denominator?
Negative x to raised to the negative 2.
Good. That's the way you've done it before. Okay. Now, if we try direct substitution here, we're not going to get a clear answer. We have to simplify this before we do direct substitution. So how can we simplify this? we can simplify this if we can rewrite the numerator so it looks more like the denominator, or if we rewrite the denominator so it looks more like the numerator. So do you recall, what did we do? How can we rewrite this so that we can simplify it?
We rewrote the top as x, x raised to the negative 1 over negative x to the negative 2.
Good. You rewrote the numerator so it looked more like the denominator. And then we had some trouble with this step, but how can we now simplify that?
We can subtract our, when we have a fraction of the exponents on top and bottom, we can subtract the exponents. So
Good.
X just X with a next, so it's just negative X. I don't know how to shortcut that.
So what should I write here?
X.
Good. Okay. You didn't sound too happy about that, but that's a good answer. That's certainly a heck of a lot simpler than this was over here, right? X to the negative 1 divided by x to the negative x to the negative 2. Now we've definitely really simplified that by subtracting the exponents.
Is there a way to work it out so that you don't have to do it in your head? Because I'm not sure how to not do it.
What were you doing in your head?
Like this one's simple because it's just x over, x basically. But if it was like 9/3 x over 3/6 x, and
maybe like this?
Yeah, like that.
Okay, sure. So the best thing to do here is, how can we rewrite the numerator so it's all one fraction? Because here we have a fraction times x to the negative 5th. How can we rewrite the numerator so it's just one fraction?
9 over...
So what I was going for is you could do this. Do you see how we could do this?
Huh.
Right? So this is just 9/3 times x to the negative 5th. So just do this multiplication, and what do you get?
9x to the negative 5th over 3.
There you go. And now how could we rewrite this so it's all one fraction?
3x to the negative 2 over 6.
By doing this. Good.
Like, I don't mean to digress anymore, but like I'm just trying to. Like, I don't feel like I'm gonna have 100%. Like on the test, I feel like there's a good chance I mess up, so I'm trying to figure out, like, if I do mess up, can I still get the problem right? So, was that a correct way to go about the problem, though?
If you what? So,
no.
so that's a good question. It's important to have a systematic approach here. So basically, it's important to know how to simplify these fractions here. So the method we're using here is the right way to simplify it. This is the only reliable way to simplify it. So these problems are giving us difficulty mainly not because of the calculus, but the algebra. This is a part of the test where you really might need to go through some of this algebra. So the only way to get these, the only way to be able to get these right reliably is to know how to do the algebra for this step. So so this is the way. So we may as well finish this off. So do you see how we got this far?
Mm-hmm.
Okay.
Yep.
Well, then what do we do now to simplify this? Here we're dividing one fraction into another. So how do you divide fractions into each other?
You subtract the exponents. So
well, this is a little too complicated to do that. Instead, we have to remember, how do you, this basically means this fraction divided by this fraction.
Okay, so you multiply by the reciprocal.
That's
so
right.
6 over 9x to the negative 5th over 3 times 6 over 3x squared and the negative squared.
And then...
Okay. I got a little away from me there. So what do I write here now?
56, wait, 9 times 54x to the negative fifth over 9x to the negative 2.
That's right. Notice this is a lot simpler than what we started with, because now we only have one single fraction. And now we can simplify some more. What's 54 divided by 9?
6.
And what's x to the negative fifth divided by x to the negative 2?
X to the negative 3.
So this is the answer here. So this is the only reliable method for doing this type of problem. So I guess there's quite a few steps until we get the hang of it. So remember that what we started with, you were saying, gee, what if I had something complicated? This was kind of dumb because I could have just, this was kind of a dumb example because we could have just reduced these fractions, right? So, if they were fractions you couldn't reduce, then you could have done it like this. Okay, so anyway, to review what we did here is, first of all, we had to simplify both the top and the bottom so that they were both single fractions. So that they looked, so we went from here to here, and here to here. And then this is something we've worked on together. We've worked on how to simplify a complex fraction. The way to simplify a complex fraction is to treat it like a division and multiply the top fraction by the reciprocal of the bottom. Okay, maybe that's something we might work on a little bit more in the future. We should probably, I think you're maybe getting a little tired, so we should wrap up the session for today. So we'll just finish off this problem. So let's see, where are we here? So going back to this problem over here, we were wondering how could you, so now here we have this problem and we're trying to simplify it. So in this case, we don't need to do any of that because there's no numbers. In this case, there's no numbers, so you can simply, so what should I write here?
Just negative x to 1, so just negative x.
That's right. We didn't have to worry about about the numbers here because there were no numbers. Okay, and now we can finally use direct substitution, and we plug in here negative 0, and we get a 0 as our answer. So we just went through the problem a second time because it gave us trouble. This would be a good problem to try maybe a third or a fourth time. So I took this problem from the website, so it seems like it would be a fair problem for the test. So I think it was largely the algebra that was giving us some trouble here. This might make more sense again tomorrow to you. It's hard. It's a lot of stuff to digest at one time. Okay, so in any case, we've been practicing this last type of problem here, this last type of L'Hopital's problem, where we're multiplying, where we end up with this new type of indeterminate form. So we have to use algebra to rewrite the expression as a fraction. And there are some problems that involve this indeterminate form on the practice test, so I think there's a good chance you'll see that on the test. Okay, so we have a little more work to finish up this section to learn those types of L'Hopital's. We're pretty close. We're close to the end of the L'Hopital's section. All right, so anyway, I think that would be a good time for us to stop here for today. It would be good to try to review some of the material that we went over today. We went over some stuff that was a little bit tricky for us, so it would be good to go back and try to redo these questions. All right, so here we have a to the negative b power. So I'd like you to move back to your screen and rewrite this in a different form. Okay. Try rewriting this in a different form on your screen.
Okay. So
Okay, good. So it looked like you used a model to help you out there. That's a good idea. So in the past, we've sometimes used numbers here, but if we have all variables, we can use that as well. Okay, that's correct. I'll go back to my screen. All right, here's another problem. Again, try writing this in a different form on your screen.
Okay.
Good. 1 over a to the first power is just 1 over a. Excellent. All right, so that's a good way to write it. I'll go back to my screen. All right, so try rewriting this on your screen in a different form.
Is that b raised to the pi?
Oh, sorry. I was trying to write a cursive C.
Oh, okay. Sorry. Yeah, that's right.
Always important to know what the symbols stand for. Okay.
Okay.
Good. That's the correct way to do that. I'll go back to my screen. Okay. Now here we have a product, and on your screen I'd like you to rewrite this as a fraction. Try rewriting this as a fraction.
Okay, so
where one of the terms ends up on the top, and one of the from the product ends up on the top, and one of the terms from the product ends up on the bottom.
Okay.
Okay. Yes, that's correct. That is a good way to write that. Although now we have a complex fraction. So let's try rewriting it one more time so that it's a simple fraction with one term on the top and one term on the bottom.
Okay.
Good. Why might that second way be better? Well, because it might be better to apply easier to apply L'Hopital's rule to it, right? It's easier to apply L'Hopital's rule if we have just power functions on the top and the bottom. But it is good to know that both of those represent the same thing. Okay, so those are both good answers. I'll go back to my screen. Now let's try rewriting this as a fraction using one of the terms on top and one of the terms on the bottom.
Down. 1 over c. Okay.
Okay. So point to the first term. You have a times b to the negative c, right? Mm-hmm. Compare that to your third term, a divided by b to the negative c. If you think about it, it doesn't make sense that those can be the same thing.
Right.
Because multiplying by b to the negative c can't give the same answer as dividing by b to the negative c. Let's maybe I'll go back to my screen and we can talk more about how to work that out. So I think the best way to have worked this out would have been first, how could you just write this term as a fraction? How would you write this term as a fraction? The term in parentheses.
1 over b raised to c.
To the c or to the negative c?
The c.
Excellent. Now how can you rewrite this as a single fraction?
We can rewrite that as a over b raised to c.
Okay, because we can just make them both into fractions and multiply through. I think this gives you a different answer than you got before.
Yeah.
Okay, so this is the safest way to work this out. So the key to algebra is baby steps. The key to algebra is baby steps. Rather than trying to jump to the answer, it's safest to do one little step at a time. So the baby step here that would have helped was before making these into one fraction, it helped just to turn this into a fraction. And when we turned this into a fraction, we saw that that when the b's on the bottom, it has a positive c exponent, not a negative c exponent. Okay, so that would be a good one to mark. That one gave us some trouble. This is pretty important in this section of the chapter. This comes up a lot, so this is important to be clear about. Okay. Does that make sense now?
Yeah, that way it makes sense. But I'm wondering, like, I know I didn't do it correctly, but I'm wondering, where did I make a mistake? Where's my mistake at? Because it feels like even with these steps, it should be right to me.
So the way you did it,
1 over.
so you did it like this, right?
Mm-hmm.
So why would we think that this? So this is different from what you did up here. If you go back and check, so here you said this was a over.
Sorry, it's 1 over b to positive c. Sorry.
Oh, you. Oh, okay, good. Sorry, thanks. Gotcha. Well, let's go back to this example. This example we got right. So this example, you started by writing it like this.
Mm-hmm.
Now notice you didn't use the same pattern here. Here, the b kept the same exponent in these two positions. But here, you changed the sign of the exponent. That's why you got the correct answer here, but an incorrect answer here, because you didn't actually follow the same pattern in both cases.
Okay.
However, that I don't really. I think this is probably not the safest way to do these problems because we don't want to. We rely just on the pattern. So here's how I should have mentioned. Here's how we should have done the previous problem. So this problem here, it would have been safest to first write. How do you just change this term into a fraction?
b over 1.
Good. How do you change it to a fraction where the b is on the bottom?
1 over b to the negative 1.
Right. And then how do you change these into a single fraction?
a over b to the negative 1.
I think that would be the safer approach for these. The safer approach is just to turn one term into a fraction, put with the b on the denominator, and then combine them. That way we have a systematic method and we're not making mistakes on those. So this one you got right, but with a method that wasn't very reliable. So I think this is a safer approach for that.
So if b negative c was that x to the negative fifth, wouldn't it be 1 over x to the fifth? The signs change?
Yes, it does, but this is, let's see. So if you had a times x to the negative fifth, that would be a times 1 over x to the fifth, which would be a over x to the fifth. But that's not the same thing as this. This is correct, but this is what you were doing. So yeah, the sign does change if you simply move the term from the numerator to the denominator. But you were doing something more complicated. You were moving the term from the numerator to the denominator of the denominator, if you see what I'm saying. And that's why the pattern wasn't working for you. So if you simply take this term here that's in the numerator and move it to the denominator, you're absolutely right. The sign does change. If you take the term from the numerator and move it to the denominator, the sign changes. But that went wrong for you because you weren't actually following that pattern. You were taking a term from the numerator and moving it to the denominator of the denominator. Well, that's too complicated to do in one step. Anyway, that's where we were getting confused. So that's hard to put into words, but do you see that distinction? Okay, so I'll erase this because that was the incorrect approach. So again, the key is to do this in little baby steps. And now if you wanted to, let's say that you wanted to turn this denominator into a fraction. How could I rewrite that denominator as a fraction?
1 over b.
That's right, 1 over b to the positive 1. So if you really wanted to write this as a fraction inside of a fraction, it's still better to do it this way, one little step at a time. The key, again, for algebra is to take little baby steps. And the same deal here. Let's say that you wanted to rewrite this denominator as a fraction. How could you rewrite that denominator as a fraction inside of the fraction?
1 over b raised to the negative c.
That's right. So notice, when you take this term from the numerator and you move it to the denominator, the sign on the exponent changes from negative c to positive c. But then, if you take the term from the denominator and move it into the denominator of the denominator, the sign changes again, and now it's back to negative c.
Okay.
All right, it's hard to put into words, but hopefully I'm showing you what the pattern is here. Okay, so because it's easy to get confused here, it's better to follow this kind of step-by-step approach. First, just turn one term into a fraction, then combine them, and then if you feel it's helpful, you can turn the bottom of the fraction into another fraction. I think usually this will be more helpful, but if you want to write it this way, it's better to do it one little step at a time. Okay, so this would all be good stuff to go back and kind of think about and practice again on your own. All right, so it's good that you asked me that question about figuring out what was going wrong there. I think hopefully now we see better what was happening. So it's good that you asked that. Okay, so let's rewrite this on your screen. Sorry, that was gh to the negative j.
J, okay. Okay. So we rewrite this as a fraction. G over 1 times 1 over hj equals g over h raised to j. G is 1 over h. Okay, cool.
That's correct. Excellent. Good. I'll go back to my screen.
Yeah, that works a lot better. I don't know what I was thinking.
So let's try this one on your screen. And again, we want to rewrite this as a single fraction with one of the terms on the top and one of the terms on the bottom.
Okay. Let's say like that.
Good. So that's pretty much the same as the previous examples. That's just more practice with that. But that is a good, safe approach. So the best way to turn this into a fraction is first just to turn the r to the negative a into a fraction and then combine them. Excellent. I'll go back to my screen. By the way, it looks like I have to work on my cursive here. This is supposed to be a cursive K, but I'll change it. Okay. I'll change it to match what you wrote. So actually, it really does look like an R, doesn't it? Okay, so much for that K. I should just write it like a normal person. Okay, so that's what the one that you did, and you got that correct. Good. A times B over C. Now let's try rewriting this as a single fraction.
Okay. Okay.
Good. That's a good way to do it one little step at a time. Excellent. I'll go back to my screen. Okay, let's try to rewrite this as a single fraction. We want to rewrite this as a single fraction rather than a complex fraction.
A over B. Okay, so Like that?
Okay, excellent. Your last two terms are the same thing, aren't they?
Right.
Okay, but that's fine. Okay, that's not what I was going for, but that was a perfectly good answer. That's not what I was going for, but that's a perfectly good answer. Let's see one other way to do this. Let's give yourself a little more space. So the way I was going for is first try to combine the two terms on the top.
Okay.
And now let's rewrite it so it's a single fraction. Okay, let's try to do this without using, so what you just wrote there is perfectly fine. That's right. That's a perfectly good answer. That's correct. However, in this case, there's really no need for negative exponents. So what I was going for instead is rewrite the bottom as d over 1 and then divide the fractions into each other.
Okay.
Okay. Do you see how that answer is a little better than the one you had gotten previously? Because it's just simpler.
Mm-hmm.
There's no confusing negative exponents there. So your previous answer was correct, but this will probably be more helpful to us in solving the problem. But you can see they're identical. All we're doing here is we took your b to the negative 1 from the numerator and moved it to the denominator, right? Mm-hmm. We know that when you move something from the numerator to the denominator, the sign of the exponent changes. Okay, so this is an important technique here, though. So we don't always have to use the negative exponents. We could just use this division of fractions, basically, to combine these. I think this is a very useful trick in many cases to combine these fractions. So again, the idea is we just multiplied the two fractions on the top, and then we divided the bottom fraction into the top fraction. Okay, so I think that would be a superior way to do this, although your first answer was correct as well. I'll go back to my screen. Okay, so let's try rewriting this as a single fraction.
So. Okay.
Excellent. Good. Now the advantage of that approach is over the one used earlier is now we don't have any negative exponents. Sometimes negative exponents are necessary, but when we can avoid them, that helps to keep the thing simpler. So that's a good approach. Good. So let's try rewriting this expression as a single fraction.
Okay, so this is just a over 1 divided by 1 half. Okay.
Excellent. That's a good method. I'll go back to my screen. Let's try to rewrite this as a single fraction.
So, A over C divided by D. Okay.
Let's see. AB over C, DF over E, ABC, DF, ABE. Okay, that's good work. That's right.
Cool.
Good. I'll go back to my screen. Okay, so notice obviously that was way simpler than what we started with. If we have something complex like this, and we can simplify it to just a simple fraction, we almost always should. That's almost always going to be a good approach to continue. Okay, try rewriting this.
Okay. Okay.
I guess what I was going for is I wanted us to simplify it.
Okay.
Okay. Notice we could have done that in one step, right?
Right.
Yeah. Okay. So I just wanted to review. This is something that when you see this, you should definitely simplify it. Try simplifying this. Okay, good. So it's important to keep track of the simple simplifications we can make as well. Good.
I was just showing mechanics. I thought that's what you wanted.
Okay,
yeah,
sorry about that. Okay. All right. Let's try simplifying this.
Okay.
Okay, good. So that's when you're dividing two numbers with the same base, you can subtract the exponents. So we haven't talked about that today, but that was a good application of that rule. Very good. I'll go back to my screen. Let's try simplifying this.
Like that?
Whoops. Okay, excellent. Yeah, it's the same thing on both the top and the bottom, so it simplifies to just 1. Very good. Let's try simplifying this.
That?
That's right. Excellent. Okay, good. So basically you're canceling the a to the negative 2's from the top and the bottom. That was correct. I'll go back to my screen. Let's try simplifying this.
Okay.
Okay, good. This is something that was giving us trouble last time, but this is an important simplification. The key technique you used here is that before you can simplify here, you had to make the thing on the top look more like the thing on the bottom. So you rearranged the 1 over a to the third so it looked like more like the a to the negative 9, and then you could combine them. That's often a good technique in algebra. If two things are different, a good way to combine them is first rearrange them so they look more similar, and then we can use the techniques we've talked about. And you were careful here with the signs, I think. So you have an a to the negative 3. Yeah, you were careful with the signs to come out with the right answer. So that's an important technique in this section. That gave us trouble last time, but that was the correct approach for that. Okay, good. I'll go back to my screen. Let's rewrite this as a single fraction.
Okay.
Good, so we just multiplied the fractions together. Excellent. I'll go back to my screen. Okay, now this one I'm going to do on my screen. Now I'm going to rewrite this as 2 fractions. So would you agree that this is legal? Would you agree this is legal?
Mm-hmm.
Okay. On the other hand, though, would you agree there's many other ways I could have done this? I could have done it instead like this. Would you agree this is also legal?
Yep.
Or, for that matter, I could have done this. Is this correct?
Yep.
Okay. How can you check these? How can you check they're correct? You check by multiplying and seeing if you get back to what you started. DE times H is this. FG times K is this. DE times H is this. FK times G is FGK. DE times H is DEH. GFK is FGK. Okay. Now, why would you want to do this? Well, sometimes it's just useful to separate things. So here's a bunch of various separations that might sometimes be useful. And you can always check them by multiplying and make sure you get back to what you started with. I'd like you to simplify this. How can you simplify that?
BDE. Do A over B times B over D times C over E.
Okay, so sorry, I didn't intend to just repeat that previous exercise. Sorry, I didn't make that clear.
Okay.
There's a very simple simplification. So if this was a real problem on a real test, you can go ahead and erase that last expression you have, A over B, B over D, C over E. I didn't make clear really what I was going for here. If this was a real expression on a real test, what's the very simple simplification you can make here?
Oh, okay. We have like that.
Excellent, good. Yeah, so that's what I was going for. Very good. I'm going to go back to my screen now. So basically you canceled the b's, right? But how do you know that you can cancel the b's? So I just want to show you how you can demonstrate that you can cancel them. You could rewrite this. Would you agree that this is legal?
Yeah.
You can check because ACB is ABC and DEB is BDE. But notice this makes clear that we really can cancel. So this is something that's given us some trouble in the past. How do you know when you can cancel and when you can't? You can cancel if you can separate the things you're canceling off into a separate fraction. You can cancel if you can separate the things you're canceling off into a separate fraction. And if you can't separate them into a separate fraction, you're not allowed to cancel. I'm not saying you have to write it this way every time. You can just cancel them in your head if that's fine. But if you're not sure, this is the way to check whether you can cancel. You can cancel when you can, and that was the point of this little exercise up here, to show all the different ways that we can separate out some of the terms. So like I said, I'm not saying you have to do it this way every time. You can do this in your head, but this is the way to check in your head to see whether the canceling is really legal. Okay.
Okay.
Let's try to simplify this.
HE. Okay, so we can rewrite this as GF over
You can go ahead.
HJ.
I'm sorry. You can go ahead and do it on your screen.
Okay.
But that's a good start.
Like this?
Okay, excellent. Now let's rewrite it as a single fraction.
Okay. Okay.
Okay. Okay, that looks good. I'll go back to my screen. Now, if you were in doubt about this problem, here's how I would have written it. The whole point of separating this is to show that we really can cancel here. -5 minus -9 is 4. And then you can combine them together again. So if you're in any doubt on this problem, here I think is a good way to write it out. Now, I'm not saying you have to write these steps every time. If you have high confidence on the problem, it's perfectly fine with me if you go straight from here to here. If you have high confidence, you can just go straight from here to here. But if you're not sure, here's the way to see that you're doing it correctly. Now, you always want to check that we're doing this correctly. If we multiplied these, we really would get back to where we started. Okay, so you got the right answer. If you, like I said, if you want to go straight from here to here, that's fine. But you should know in your head that this is what we're really doing. And this is how you can do it on paper if there's a problem that's giving you some difficulty. Let's try simplifying this expression.
minus C is 7. Like that?
Okay.
I think I wrote my B back. No, it's just left.
Okay, good. I think, yeah, okay, good. All right, so that was a good process, and you got the correct answer there. Very good. I'll go back to my screen. That was a good process. There was a point where you weren't quite sure, but you took your time and thought about it. That was a good process. That might be the best process. Let me show you one alternative approach. An alternative approach would be see if you can see how I went from the left-hand side to the right-hand side here.
Mm-hmm. Yeah, I was thinking about doing that, and then I swayed away for some reason.
And does this step make sense?
Mm-hmm. Yeah, that's better.
And does this step make sense?
Mm-hmm.
And I think I ended up with the same exact answer that you got.
Mm-hmm.
Okay. Now, I'm not saying, I don't know, I don't actually have a strong opinion about which way is better. I just wanted you to see both ways, and then it's up to you. So both of these are perfectly good approaches. The way you did it was perfectly good, but I wanted to demonstrate this way as well. So you have both of them in your toolkit, and then you can use whichever you feel more comfortable with on the individual problem. But it's good to be familiar with both approaches.
I'm going to just copy
Sure.
this down. B over C.
Tell me when I should scroll.
I can scroll to the right a little bit. Good. Wait, so we had AB. Okay, we multiplied by the reciprocal. So we have ABC to the over. Okay, cool. Yeah, that's good. Thank you.
All right, so those would both be good to like I said, both of those are good approaches. You can use whichever feels more comfortable to you. All right, let me write this down. This is a -6.
Okay.
It's hard to distinguish 6 from a B. And this is a 4, not a Y. It's hard to distinguish 4 from Y. Okay, let's try so let's try simplifying this. Use whatever method you feel most comfortable with to simplify this expression.
Okay, so I'm going to try and make fractions. So there's 1, and then there's 1. Four minus 6. So G F D to the -6. Okay, so H over D to the 4th, G F over D to the 6th, G F over D to the 6th times reciprocal, G F D to the 4th over D to the 6th of H, and then we have G F over H times
Yes. 4 minus 6, -2. GFD -2 over H. And then I guess this is the simplest form without a fraction.
Okay, good. That's a good approach. That's a good method, and that's a good answer. Let's see, can you rewrite that without a negative exponent?
Okay. Like that?
That's a good step. Now can you rewrite it so it's a simple fraction instead of a complex fraction, but still without a negative exponent? So how can we simplify this without putting in a negative exponent?
Like that?
Okay, excellent. Good. That really is simpler, right? Good.
Mm-hmm.
So that stumped you a little bit. You took your time and you figured it out. Compare that to the answer that you have. Point to the answer that has the star. Notice with practice, people could just go straight to the other answer. Notice that all that you did is you moved the d to the denominator. As we've talked about in the past, when you move a variable to the other side of the fraction, the sign of the exponent changes, right? If you compare those two, you just move the d from the top to the bottom and the sign of the exponent changed. But it is best to kind of work it out step by step to make sure you're not making any mistakes. And now we ended up with a slightly simpler answer. So this would be a good one to mark and go back and think about again later. So your first answer was a good one, but it's good to be able to know how to go even further with the simplification on that. Let's actually stay on your screen for a moment. Go back to the beginning of the problem. If we can find it.
Right
where did we start here? Okay, yeah. And then you did, so h to the 6th. Okay, excellent. Very good. I'll go back to my screen. Now, overall, that was a good approach. That was a good approach and a good method. I'm going to show you one other approach here to have in your toolkit. How can I rewrite this so it's not a fraction?
Oh, d to the -4th.
Right. And then we could write this. What does this simplify to?
D to the -2.
Good. So that's basically the first answer that you got. So this is just another approach. And if I want to get rid of the negative exponent, how can I rewrite d to the -2 so it doesn't have a negative exponent?
1 over d squared.
And now how can I write this so it's a single fraction?
GF over HD squared.
Okay, so this is just another approach that maybe is a little bit simpler. So you can, again, have this in your notes and kind of think about how we did this. So what you did is you changed this to look like the bottom term, 1 over d to the 6th. But maybe it would have been simpler to change the bottom term to look like the top term. But I'm not saying your method was wrong, but it's good to know both approaches. Okay, so do you have that in your notes?
Yep.
Okay, so that's a good approach, again, to go back and think about, and then we ended up with that answer there. Okay, good. This is a negative 5. So let's try to simplify this expression.
Okay. -5 minus -5 is -5 plus 5. So 0, C, 0 is 1. So just AB over GH.
Good. Basically, you have the same term on both the top and the bottom, so they cancel. Notice that you you use the subtraction rule, and you just confirm that that just matches the general canceling approach here. You saw that they have the same term on the top and the bottom, so you could just cancel them, or you could use the subtraction rule to show that. Because what's -5 minus -5?
0.
And what's c to the 0 power?
1.
So that term would disappear. Okay, good. So you ended up with the correct answer there. Good. I'll go back to my screen. That was good. This is a -4.
Okay.
So let's try simplifying this expression.
Okay, so first I'm going to make this F, C, 4. This. Oh. -4 plus 4. So just F. So negative AG over F.
Okay. This was pretty much similar to the previous example, but with a negative sign. You handled that correctly. So it's important to see when you can cancel terms. Good. So let's go back to my screen. One way to think about this is, would you agree that we could rewrite the original expression like this?
Yep.
And then it's pretty obvious that these cancel.
Mm-hmm.
So I notice you're using a subtraction technique. -4 minus -4 is c to the 0th power, and that's 1. So that's perfectly fine, but it's also perfectly acceptable just to cancel them. Okay, good. But it's good to see that both of those approaches give you the same answer. Okay, good. Let's simplify this expression.
So we get -7 plus 3 x to the -4th, and then -6 divided by -1. So that, and then this equals natural log of x. Natural log of x over this is 6 over 1 times 1 over x to the 4th, 6 over x to the 4th. Equals x to the 4th on bottom. Okay, so x to the -4th is this. 6 is 6 over 1. 6 over 1 times 1 over x to the 4th equals 6 over x to the 4th. And then I brought it to the bottom. I would just stop here and try and solve the problem. I'm not sure where to go.
Okay. So where would you stop?
Right here.
Okay. Let's see. Up until the last step, that was an excellent process. Up to the last step, that was an excellent process. Then we had some trouble there at the end. Okay, so I'll go back to my screen. So I think this was what you had gotten in the next to last step. And your process up to there was very good. Now, is this true or false?
It's true.
Now, how could I rewrite the bottom of this fraction as another fraction?
1 over x to the -4th.
Here's where you're getting confused, though. What you wrote was this. This is the same issue we had at the beginning of the session today. You're saying, oh, if I put this in the denominator, I have to change its sign. But you're not just putting it in the denominator, you're putting it in the denominator of the denominator. So you should really change the sign twice and get back to where you started. So this is what you did. This is and this is incorrect. This would be the correct approach. So notice if you actually rewrite it like this, you go back to x to the -4. If you see what I'm saying? There was an x to the -4 here. When you move it to the denominator, it gets a positive exponent.
Right.
But then if you decide you wanted to put it in the denominator of the denominator, the sign changes again, and it goes back to being a negative exponent.
Okay.
Now, really, that's really probably not the best approach then for this problem. A better approach would be this. How can I rewrite this as a fraction?
Natural log of x.
Sorry, how can I rewrite just the x to the -4 as a fraction?
One over x to the 4th.
That's right. Not 1 over x to the 4th. This would be wrong. This is kind of what you were doing. What you were doing was this, but this is the correct way to write it. And now how can I rewrite this whole expression as a single fraction? we rewrite this whole thing as one single fraction?
Natural log of x times 6 over x to the 4th.
That's right. You just multiply 3 fractions in a row. You might want to compare this to the answer that you got before. So the answer you got was something like this. So, so we ended up with an incorrect answer before. For one thing, there's no need to move the 6 along with the x to the 4th. I think that was one of the main things that was confusing you. You were trying to move the 6 and the x to the 4th at the same time, but why not just treat those as 2 separate terms? That's the key thing that I did here. I just treated the 6 as a separate term from x to the 4th and just left it on the top of the fraction. So it's good to study how that, again, the key here is to take little baby steps. What we want to do is get rid of this negative exponent. The 6 is fine. We want to get rid of the negative exponent. So we just rewrote that as 1 over x to the 4th. And then we got this term. So the mistake that you were kind of making is that you're, instead of putting the x in the denominator, you're putting it in the denominator of the denominator. And that's more complicated than we really need here.
Right, I'm just not seeing how and when I make the mistake.
Does this approach here make sense?
I'm still confused, to be honest.
Okay. Let's see. So here's the answer that you got.
Okay.
Do you see how I went from here to here? Actually, let's do it like this. So here's the answer that you got. And now do you see how I went from this term to this term?
Mm-hmm.
Yeah. Notice I didn't change the log x because there's no problems with it. I didn't change the 6 because there's no problems with that. I just changed the x to the negative 4th to get rid of the negative exponent. Now, what you should not do is this. Here's what you're kind of doing. You're doing this. And this would be a mistaken approach. We're not putting the x in the denominator of the denominator. We're just putting it in the denominator. Okay.
Was that what I was...
Well,
yeah.
Basically, you were kind of doing that, but you were also trying to do a bunch of different steps in your head. You were trying to write it all in one fell swoop, when it's really safer just to first write only this term as a fraction. Not the so one thing that was confusing you was trying to move the 6 around at the same time, but we can just leave the 6 where it is and just change this term into a fraction.
Okay.
I guess basically I can't quite say what your mistake was because you kind of you combined a couple steps into one step. So it's better to do fewer steps at a time. And now how can we rewrite this as a single fraction?
What we have to the right.
Yeah,
so
you just treat them as 3 separate fractions and multiply them together. Okay, so this would be a good one to go back and take another look at, because there's some problems that I really don't think we can solve if we leave them in this form. We really do have to make this simplification. So the problem is that with L'Hopital's rule, there are some simplifications that have to be made in order to get the problems right. Okay, so these are not optional simplifications. Okay, so then we ended up with this answer here. So the key thing was just take one little baby step. Just change the x to the negative 4 into 1 over x to the 4th. There's no need to drag the 6 along with it, or the natural log, and then we can combine those into a single fraction. Okay? Okay. So let's try to rewrite this, simplify this.
Like that?
Excellent. Very good. So that was very similar to the previous problem, but that was the correct approach. Excellent. Good. I'll go back to my screen. Okay, so here's one of the intermediate steps that you had gotten. Since we're so you did that correctly, but since these are giving us trouble, I would have separated it out into slightly smaller baby steps. First, I would write this. So the point is, we're trying to write only things that we're trying to not memorize any steps, but only do things where we can clearly see why it's algebraically justified, so that we're not just memorizing a pattern. So here's the one step that you left out. So it's good that you moved the 8 to the front. The one thing I would do is first just rewrite this as a fraction, and then I would combine them together to get the answer, just so that you can see what the reason is, why this works, rather than just relying on a pattern here. And then you did get the right answer. So that was a good method, and you did get the right answer. But since these are giving us trouble, it would probably be better to include this one extra step. Let me remind you what you would tend to do in the past on these problems is you would tend to write something like this. This is kind of the mistake that you were tending to make before. But if we take it one really little step at a time, we're not going to make those mistakes. Okay. Okay, good. So that was a good approach on that problem. Okay, try simplifying this expression.
One second. Glasses. Okay. Okay.
Okay, let's go back to my screen. Let's do this on my screen. How could we rewrite this expression?
xy plus xz.
That's the distributive law. Good. How could we rewrite this expression?
xyz.
Notice you don't use the distributive law.
Mm-hmm.
There's no distributive law over multiplication, is the point. There's no distributive law over multiplication. These parentheses are just unnecessary in this case. In this case, we just get rid of the parentheses. Now, maybe, I'm not sure if you could read my writing here. So this is a multiply sign. Was that clear?
Mm-hmm.
Okay, good. But I think that you ended up trying to use the distributive law here.
Mm.
Let's try this. How could you rewrite this?
xyzw.
You just get rid of the parentheses. There's no distribution that's occurring here. Distribution only occurs over addition, not over multiplication. These are just unnecessary parentheses. So our approach for this problem turned out to be incorrect because I think you tried to apply the distributive law there. Let's go back to your screen. Okay. Yeah. So notice you were trying to distribute the b over the c and the d. But that would only work if that was an addition rather than a multiplication. So let's try that again.
Like that?
Good. So the point is the parentheses in this case were just unnecessary. The parentheses were just unnecessary. There was no distribution here because there was no addition. So we should just rewrite it without the parentheses, and then that shows us that we can cancel. That would be a good one to mark, and maybe make a note that we should not use the distributive law on that example. After all, take a look in the previous example. Notice in the previous example, you had cosine x, parenthesis, 8 times x to the negative 6. But you didn't distribute the cosine x over the 8 and the x to the negative 6. That previous example was actually very similar to this example, and that one we got correct. Okay, I'll go back to my screen. So let's try simplifying this.
Like that.
Okay, right. So the point is the parentheses are irrelevant. You can just cancel the y's in that case. Very good. I'll go back to my screen. Let's simplify this.
A, B, D, C to the 6.
What was your answer?
A, B, D, C to the 6.
Okay. So again, the parentheses are irrelevant. And we can just simplify that. Okay, excellent. Can we cancel the a's here?
We can't.
I'm sorry, did you say yes or no?
No.
No, you cannot cancel them. Can you cancel the a's here?
Yep.
Yeah. Here's how you can see that you can cancel. First, you could write this. Then you could write this. And now it's clear that we can cancel. I'm not saying you have to write it out this way, but when you're not sure whether you can cancel or not, the safest thing is to make sure you can rewrite the fraction so the two things that you're canceling are all by themselves, like this. If you can rewrite the fraction so the two things you're canceling are all by themselves in a separate fraction, then you can clearly cancel them. But there would be no way to do that with this expression. There's no way to rewrite this so that there's an a to the a all by themselves, because there's no way to factor an a out of the top term. So like I said, I'm not saying you have to rewrite all these steps every time, but when you're in doubt about whether you can cancel or not, this is the way to prove to yourself whether you can cancel. You can cancel if you can rewrite the things you're canceling all by themselves in a separate fraction. We couldn't do that here, and that's why we couldn't cancel. Okay, all right. Well, so those are things that have been giving us some trouble for a while, and hopefully we've cleared up some issues there. There's a lot of fractions in this course, and a lot of cases where it's helpful or necessary to simplify. So that was a very quick review of some important stuff. This is an important part of your notes to hang on to and review every once in a while. This is necessary for this part of the course, but this should be helpful for the rest of this math course. There's lots of fractions in the rest of this math course, so it's really important that we understand the algebra for those types of fractions. So this would be good stuff, like I said, to hold on to in your notes. I think you mentioned that you got tons and tons of notes now. This would be an important part of your notes not to get mixed up with the other parts of notes. This is something that would be good to hold on to and keep reviewing. It might be helpful to review when you're starting other science classes too, because this is all math that can be very helpful, say in physics or chemistry or whatever, this basic algebra of fractions. So hopefully now this is all in your notes and you can hold on to those notes and review it as the course goes on, or when you take another math course, or also when you take another course, and obviously review for the test that's coming up, because some of these, a lot of these issues are things that I think are necessary for some of the problems on the test. Okay, so we went through that pretty quickly, so hopefully you'll have the time at some point to go back and get more comfortable with those ideas. But I think we made some important progress on that algebra. So let's try this problem on your screen.
First, it says okay. I'm not sure.
Okay, actually that first expression you had was pretty good. So let's rewrite that first expression that you had. Good. Now how can you rewrite the 1 over x so that it's not a fraction? And let's put that all in parentheses with the prime since we haven't taken the derivative yet. So how can we rewrite the 1 over x so it's not a fraction?
I'm blanking out.
Okay, I'll go back to my screen and give you some help with that. So remember, 1 over x is x to the negative 1. What's 1 over x squared? How could we rewrite that so it's not a fraction?
X to the negative 2.
Good. How could we rewrite this so it's not a fraction?
X to the negative 5.
Okay, so these are some things that we can do to rewrite expressions so they're not a fraction. So how can we rewrite 1 over x so it's not a fraction?
X to the negative 1.
Okay. How can we simplify the interior of this parenthesis?
We can write it as 3x to the negative 1.
Okay. Do you know how to take this derivative?
But you bring 3 out, 3 on the outside.
You could if you wanted to. Okay, that's the constant multiple rule. So what should I write here?
Negative x to the negative 2.
Okay, so what's the full thing I should write here?
3 times negative x to the negative 2.
Good. So that's just our standard power rule, right? What's this derivative?
5x to the 4th.
Right, that's just the standard power rule. What's this derivative?
12x squared.
Right, that's just the standard power rule. So that's what we were applying here. That was the advantage of rewriting this as x to the negative 1. The advantage of rewriting it as x to the negative 1 is now we can apply our standard power rule. So sometimes it's helpful to get rid of negative exponents. I can see how this can be confusing because sometimes it's helpful to rewrite something without a negative exponent. Sometimes it's helpful to rewrite it with the negative exponent. We have to use judgment and trial and error to decide which is the expression that's going to be most convenient for us to use. So we ended up here with negative 3x to the negative 2. Okay, so the key thing here was, of course, another thing you could do is you could have used the quotient rule.
Yeah.
However, that would be kind of massive overkill. You could use the quotient rule, but that would be quite complicated. This should really be a simpler approach. The point here is that we can rewrite this then so that x is just a normal power function. And then we can use our derivative rules. Okay, so let's try this problem on your screen.
That.
Okay, excellent, good. That looks right. By the way, then, if you wanted to rewrite that without the negative exponent, it might or might not be helpful, but let's rewrite that now without a negative exponent.
Okay. Like that.
Okay, that's right, good. I'll go back to my screen. Now again, the way to build your confidence here is not to skip steps so that you can see the rationale for these steps. So we could start by rewriting this like this. This is clearly legal. Then we could rewrite it like this. It should be obvious that this is legal. Then we apply the power rule. And now here's a step that you skipped that I think would build your confidence if you included it. Just deal with the x to the negative 2 to start with. So hopefully it's clearly legal that we can go from this to this. And then now we can combine these. I think the thing that's kind of messing up our confidence sometimes is trying to go straight from here to here. I think it would be better to show this intermediate step so we have more confidence that we're doing things that are clearly legal rather than just trying to memorize patterns. The mistake is just to try to memorize patterns because there's too many patterns and they get confused with each other. Instead, if we can break this up into really small steps that are obviously legal, then we can see that we're getting the right answer. But anyway, you did get the right answer there. That was correct. So that was the correct way to do that. So let's try this.
Like that.
Excellent. Okay, that's a good process. That might be a good answer right there, but if you wanted to get rid of the negative exponent, let's show how we would do that.
That.
Okay, good. That's correct. I'll go back to my screen. So that was a good process. I'm just going to write it out again, showing a few more of the steps that might be a little bit safer for us because our confidence is not very high here. here's a step that might have been good to show. Here's how we can really break these apart. It should be clear that this times this equals this. And then we get to here. So you just went straight from here to here. Maybe it's a little bit better to show this step because our confidence is not too high right now, and this is a way we can see more clearly why this is legal. Then you got to here. And again, here's a step that you skipped when you worked it out. Maybe at this point it would be a little bit better to show this step, though, because we were making some mistakes before. And here's the answer that you got. So when you did it, you went straight from here to here, and you got the right answer, so that was a good process. But since our confidence is not very high here and we're sometimes making mistakes, it might be better to force ourselves to make smaller baby steps and include this step here. That way we're not just trying to memorize the pattern, but we're seeing why this technique works. But that was correct. You got that answer correct. Let's try this.
Okay.
How did you get that 0 at the end as your answer?
Secant of 0 is 0.
Did you do that from memory or on your calculator? Now, I think what happened here is I think sometimes in the past we've confused secant and sine, and I think you might be doing that here. Remember that the secant is not the same thing as the sine. So we actually haven't worked with secant for a while. Do you remember how we could work with secant here? Do you remember what that means?
No, I don't.
Okay, so let's go back to my screen and talk about that. Let's put that problem aside for a moment. So what does secant of x mean? It means 1 over cosine x. So this is something that we need to have memorized for the test. We haven't talked about this for a while, but there were some examples that involved this on the sample test that you sent me. So secant of x means 1 over cosine x. Secant is not the same thing as sine. We don't want to confuse those with each other. Okay. So let's try this problem.
1.
Okay, how did you work that out?
1 over cosine of 0 is 1 over 1. Just 1.
Okay, that's right. Notice it's not 0. It turns out to be 1. Okay, good. So let's go back to this expression and try this.
I think that's the same problem, right?
Well, here this was secant of 0, and this is the limit of secant x as x approaches 0. So they're certainly going to be similar, but they're not the same exact problem. Before we could go over how to do the limit, we had to review what secant meant.
Like that?
Okay, that looks good. I'll go back to my screen. So you're using here the direct substitution approach. Now remember that once we use direct substitution, we shouldn't be writing LIM anymore. So I'm not going to write LIM here because we're using direct substitution. And I'm going to show a little bit extra of a step. Secant of 0 is 1 over cosine of 0. 1 over cosine 0 is 1. So this would be the best way to have it out in your notes so that you can review this later and see how we got to the answer. So notice we don't write LIM at this step because we're doing direct substitution. And then this is how we could work it out in your notes so that when you review this later, you can see what the steps are for that. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. there's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.